Look up at the night sky. See those points of light, those shimmering stars. That is our local cosmic neighborhood. But if you could keep going, past the familiar constellations, past the faint glow of the Andromeda galaxy, and journey for billions upon billions of light years into the deepest, most profound emptiness imaginable, you would eventually reach the absolute frontier, the very edge of our observable universe. And there, in that crushing, primordial darkness, lurk some of the most enigmatic and powerful objects in all of existence. What secrets lie hidden within the absolute darkness at the edge of everything we can see? These are not merely empty voids. They are the universe's most distant black holes, cosmic leviathans so ancient that their light has been traveling across the cosmos since the universe itself was in its chaotic infancy. To observe them is to look back in time to an era when the first stars and galaxies were just beginning to flicker on, a chapter of cosmic history written in the silent, gravitational signatures of these colossal entities. We are about to embark on an extraordinary journey to uncover 30 incredible facts about these far-off giants. This is not just a catalogue of distant objects. It is a voyage to the very limits of our understanding, a deep dive into the methods and technologies that allow us to detect the undetectable. We will explore how astronomers use the subtle warping of light, the faint screams of energy from quasars, and the very fabric of space-time itself to find these shadows at the edge of sight. The existence of these supermassive black holes so early in the universe's life presents one of the greatest puzzles in modern astrophysics, challenging our fundamental theories of how such immense structures could form with such astonishing speed after the Big Bang. They are not just dead ends in space, they are active, dynamic engines that shape the cosmos we live in today. So prepare to have your perspective shifted. We are going to journey beyond the familiar, beyond the local, and into the realm of the truly ancient and mysterious. From the techniques that bring them into focus to the profound questions they still pose, each fact will pull back another layer of the cosmic veil, revealing a story of gravitational dominance, ancient light, and the relentless human curiosity that drives us to peer into the deepest dark. This is an exploration of the universe's most distant black holes, and the journey is just beginning. To truly grasp the nature of these far-off giants, we first need to understand what we mean when we call them the most distant. It sounds straightforward, but in our expanding cosmos, distance becomes a deeply complex idea. We are not talking about a static measurement like the miles between two cities on a map. The universe itself is stretching, carrying galaxies along with it like raisins in a rising loaf of bread. This expansion fundamentally changes the meaning of distance. So when astronomers pinpoint a black hole 13 billion light-years away, that number represents more than just a vast span of space. It signifies an immense journey through time. Because light, while incredibly fast, has a finite speed, it takes time to travel across the cosmos. The light arriving at our telescopes today from one of these distant black holes set out on its journey billions of years ago. We are not seeing the object as it exists now. We are witnessing a snapshot from when the universe was a fraction of its current age, a cosmic fossil preserved in the fabric of incoming radiation. This concept of looking back in time is powerfully quantified by a phenomenon known as redshift, symbolized by the letter Z. As light travels through the expanding universe, the space through which it moves is stretching. This stretches the light waves themselves, making them longer and shifting them toward the red end of the electromagnetic spectrum. The greater the redshift, the more the light has been stretched, and therefore, the longer it has been traveling and the farther back in time we are looking. A high redshift value is like a timestamp, telling us we are observing an object from the universe's early epochs. Some of the most distant black holes we've detected have redshifts so high they correspond to a time when the universe was less than 10% of its current age. They are not just old, they are primordial relics from a time of cosmic dawn. This makes these black holes far more than just exotic celestial objects. They are unparalleled time capsules. By studying them, we are effectively conducting archaeology on a galactic scale, peering into the conditions of the infant universe. Their very existence so early in cosmic history challenges our understanding of physics, forcing us to ask fundamental questions. How could such incredibly massive objects, often weighing billions of times the mass of our Sun, form and grow to such immense sizes in what was, cosmically speaking, the blink of an eye after the Big Bang? The light from these distant quasars and active galactic nuclei carries encoded information about the composition of the early universe, the density of matter, and the mechanisms of gravity operating under extreme conditions. Each photon is a messenger from a bygone era, carrying secrets about how the first structures in the cosmos came to be. Now, let's meet the current champion of cosmic distance, a quasar known by its catalog name J0313-1806. This is not just another entry in an astronomical database. It is a profound outlier, a beacon from a time so early that its very existence strains our understanding of cosmic evolution. The light we are capturing from J0313-1806 today began its journey to Earth when the universe was a mere 670 million years old. To put that into perspective, our cosmos is approximately 13.8 billion years old today, meaning we are seeing this object from a time when the universe was less than 5% of its current age. It is a direct window into the epoch of reionization, a period when the first brilliant stars and galaxies were burning away the primordial fog of hydrogen gas that filled the young cosmos. But the sheer distance and age of this object are only part of what makes it so astonishing. The true shock comes from its immense scale. At the heart of this quasar lies a supermassive black hole with a mass calculated to be over 1.6 billion times that of our own Sun. Let that number sink in for a moment. Our entire solar system, with the Sun and all its planets, fits comfortably within the gravitational grip of a single object that is over 1 billion times more massive. This Leviathan did not just appear out of nowhere. It had to form from something, growing from an initial seed into a cosmic titan in less than 700 million years. This presents an almost insurmountable challenge to our standard models of black hole formation. One leading theory suggests that the first black holes grew from the collapsed cores of the very first incredibly massive stars. These would have been behemoths, perhaps hundreds of times the mass of our Sun. But even starting from such a massive seed, the process of accreting enough gas and dust to reach over 1 billion solar masses in such a short time seems almost impossibly fast. The black hole would have needed to consume material at or near its theoretical maximum rate, known as the Eddington limit, for its entire existence without pause, a feeding frenzy of almost unimaginable intensity and duration. This forces astronomers to consider even more exotic possibilities. Could the seeds for these supermassive black holes have been formed through the direct collapse of enormous clouds of primordial gas, bypassing the star formation stage entirely and creating black holes that were already tens of thousands of times the mass of the Sun from their very first moment? Or did they grow through a frenzy of rapid mergers in the dense, crowded environments of the first proto-galaxies? The existence of J0313-1806 is a massive, glaring clue that our current story of cosmic structure formation is incomplete. It tells us that the conditions in the very early universe were far more extreme and efficient at building colossal structures than we ever anticipated. This single point of light, which has been traveling for over 13 billion years to deliver its message, fundamentally challenges us to rethink the very first chapters of our cosmic history and the physical laws that govern the dawn of time. With such a colossal object as our previous record holder, a pressing question naturally arises. If black holes are, by their very definition, black and invisible, how on earth do we detect something so faint and far away? The answer lies not in observing the black hole itself, but in witnessing the spectacular cosmic drama that unfolds around it when it decides to feast. We are able to see the unseeable by observing the most luminous and persistent sources of light in the entire universe, known as quasars. The term quasar is actually a shortening of quasi-stellar radio source, a name given because when they were first discovered, they appeared as star-like points of light in optical telescopes, yet they emitted powerful radio waves. We now understand that a quasar is not a star at all, but the intensely bright, active core of a distant galaxy, powered by a supermassive black hole in the midst of an epic feeding frenzy. Imagine a black hole with a gravitational pull so powerful that it draws in vast clouds of gas, dust, and even entire stars that wander too close. This material doesn't fall directly into the black hole's event horizon, the point of no return. Instead, it forms a swirling, flattened, superheated structure known as an accretion disk. Think of water spiraling down a drain, but on a cosmic scale and at velocities approaching the speed of light. The particles of gas and dust within this disk are subjected to immense frictional and gravitational forces, colliding with each other with such violence that the temperature soars to millions of degrees. Matter this hot doesn't just glow, it blazes, emitting a ferocious torrent of radiation across the entire electromagnetic spectrum, from high-energy X-rays and ultraviolet light down to visible light and infrared. This process converts gravitational energy into light with an efficiency far beyond that of nuclear fusion, which powers ordinary stars. A single, actively feeding supermassive black hole can outshine every single one of the hundreds of billions of stars in its host galaxy combined, becoming a beacon visible from the farthest reaches of the cosmos. This is the fundamental trick astronomers use. We cannot see the black hole's shadow, but we can easily detect the brilliant, pinprick glare of its accretion disk from billions of light-years away. The light from a distant quasar is so concentrated and powerful that it can drown out the faint, diffuse light of its entire host galaxy, making the galaxy itself virtually invisible next to its brilliant central engine. By training our most powerful telescopes on these points of extreme luminosity, we are effectively using the black hole's own energetic feast against it, turning its consumption into our observation. The specific colors or wavelengths of the light emitted by the accretion disk also carry a wealth of information. By analyzing this spectrum, astronomers can determine the composition of the material being consumed, the immense speeds at which it is orbiting, and crucially, the mass of the central black hole itself, calculated by observing how its gravity influences the frenzied motion of the surrounding material. So, every time we identify a distant quasar, we are not just finding a point of light, we are uncovering a cosmic signature, the telltale glow of a supermassive black hole actively shaping its corner of the universe. But even with the incredible luminosity of quasars, there's a limit. As we peer deeper into the cosmos toward the very first black holes, their light becomes so faint and stretched that it begins to fade into the background noise of the universe. So how do we push past this observational frontier? Nature itself provides a spectacular solution, a cosmic trick of light predicted by Albert Einstein's theory of general relativity over a century ago. This phenomenon is known as gravitational lensing, and it acts as a natural telescope gifted to us by the fabric of space-time itself. Einstein revealed that gravity is not just a force between objects, but a curvature in the very fabric of space and time. Imagine space-time as a vast, taut rubber sheet. When you place a massive object like a star or a galaxy on that sheet, it creates a dip, a gravitational well. Now picture light traveling across this curved sheet. It doesn't always move in a straight line. Instead, it follows the bends and curves of the sheet. When light from a distant object like a quasar passes near a massive foreground object like a galaxy cluster, its path is bent. This is gravitational lensing in its essence. The gravity of the foreground mass acts as a lens, warping and distorting the light from the source behind it. This cosmic lens can produce several astonishing effects. Sometimes it simply magnifies the background object, making it appear brighter and larger, just like a magnifying glass focuses sunlight. This is an invaluable tool for astronomers. A distant, faint quasar that would be a mere speck of light in our most powerful telescopes can be amplified dozens of times over by a perfectly aligned foreground cluster, bringing it into clear view. In other, more dramatic cases, the alignment is so precise that the lens doesn't just magnify the light, it multiplies it. We see multiple images of the same single quasar, stretched and smeared into luminous arcs and crosses around the central lensing cluster, a phenomenon known as an Einstein ring. These cosmic mirages are not only breathtaking to behold, they are powerful scientific instruments. By carefully studying the shape, brightness, and arrangement of these lensed images, astronomers can perform extraordinary feats of cosmic deduction. They can map the distribution of both visible and invisible dark matter within the lensing galaxy cluster, as it is the cluster's total mass, including the dark matter, that bends the light. Furthermore, this natural magnification allows us to see intricate details in the distant quasar's host galaxy that would be utterly impossible to resolve otherwise. We can study the structure of its accretion disk, observe clumps of gas falling inward, and gain unprecedented insights into the environment around these infant supermassive black holes. Gravitational lensing effectively turns entire galaxy clusters into the most powerful telescopes we could ever hope for, with apertures hundreds of thousands of light years across, allowing us to gaze directly into the cosmic dawn and witness the formation of the very first monsters of the universe. This central puzzle is perhaps the single greatest challenge these distant black holes present to modern astrophysics. How could an object accumulate over 1 billion times the mass of our Sun in less than 700 million years? When you break down the timeline, the numbers simply don't add up under our conventional understanding. Let's consider the standard model of black hole growth known as Eddington limited accretion. A black hole feeds on surrounding gas, but this process isn't silent. The intense radiation pouring out from the hot accretion disk actually pushes back on the infalling material, creating a natural balance, a maximum sustainable feeding rate. For a black hole to grow by steadily pulling in gas at this maximum rate, it would take nearly 800 million years just to grow from a 100 solar mass seed to 1 billion solar masses. But our record holder, J0313-1806, achieved this and more in even less time. It's like finding a toddler who weighs as much as a professional sumo wrestler. The growth rate we're observing defies all standard developmental milestones. This glaring discrepancy has forced astronomers to think far outside the box, proposing several radical theories to explain these cosmic overachievers. One compelling idea is the direct collapse model. This skips the star formation phase entirely. In the very dense, pristine environment of the early universe, enormous clouds of pure hydrogen and helium, uncontaminated by heavier elements, could have collapsed under their own gravity directly into a black hole. This wouldn't create a small stellar remnant, but a colossal seed right from the start. A black hole already boasting tens of thousands or even hundreds of thousands of solar masses. With such a massive head start, growing to 1 billion solar masses within the available time becomes a much more feasible, though still staggering, task. These direct collapse black holes would be the true primordial giants, born large rather than growing large. Another fascinating possibility reaches back to the universe's very first moments. What if the seeds for these supermassive black holes weren't formed from stars or gas clouds at all, but were instead forged in the incredible furnace of the Big Bang itself? These would be primordial black holes created by the extreme density fluctuations in that initial explosive expansion. While most theories suggest such objects would be small, some could have been born with significant mass. If a sufficient number of these intermediate-sized primordial black holes existed, they could have served as the foundational seeds, merging and accreting material rapidly in the crowded early galaxies to build the behemoths we observe. There's also the scenario of super-Eddington accretion, where a black hole gorges itself in a spectacular binge, perhaps in the uniquely dense conditions of the early cosmos, with gas clouds packed tightly together. Black holes could temporarily consume material at rates far exceeding their theoretical limit. This wouldn't be a gentle, steady rain of gas, but a violent, chaotic downpour where radiation pressure cannot effectively hold back the flood of incoming matter. This duty cycle of intense feasting followed by quieter periods could allow for much faster overall growth, like an athlete combining short bursts of extreme training with longer recovery phases. Each of these theories has its own strengths and its own set of challenges, and the truth may involve a combination of these mechanisms. The existence of these distant black holes is a clear signal that the early universe was a far more volatile and efficient nursery for cosmic giants than we ever imagined. They stand as monumental clues, compelling us to rewrite the story of cosmic dawn and reconsider the fundamental processes that built the largest structures in our universe. So we're faced with this cosmic timing problem, a puzzle written in the light of these ancient quasars. The solution, many astronomers believe, lies not in the growth phase itself, but right at the very beginning in the nature of the original seed. Think of it like planting a tree. If you want a giant redwood to reach its full height in a very short amount of time, you don't start with a tiny acorn. You start with the largest, most robust sapling you can find. The same logic applies to the universe's first black holes. The type of seed they grew from dictates their entire life story and determines whether they could have become supermassive in those first few 100 million years. The traditional, and for a long time the most accepted, model begins with the death of the very first stars. These weren't anything like our stable, long-lived sun. Theorized to be colossal beasts, these population 3 stars were composed purely of hydrogen and helium, the pristine elements forged in the Big Bang. Without heavier elements to help cool them and regulate their burning, they could grow to staggering sizes, perhaps several hundred times the mass of our sun. Such massive stars live fast and die young, burning through their nuclear fuel in just a few million years. Their death is not a quiet fade but a spectacular supernova explosion of unimaginable power, known as a pair instability supernova, which can completely tear the star apart. But in the most massive cases, the core collapse is so extreme that it bypasses the explosion entirely and collapses directly into a black hole. This process creates what we call a stellar mass black hole seed, likely weighing in at anywhere from a few dozen to perhaps 100 solar masses. It's a substantial object, to be sure, but from this starting point, growing to over 1 billion solar masses is a tremendous, almost impossibly slow climb, like trying to fill an Olympic-sized swimming pool with a garden hose. This is where the more exotic and increasingly favored model comes into play, the direct collapse black hole. This theory proposes a shortcut, a way for the universe to build a giant seed without ever going through the star-making process. Picture the early cosmos, a vast, dark, and relatively smooth sea of primordial gas. In certain rare regions where the gas was particularly dense and rapidly collapsing, something extraordinary could happen. As this enormous cloud of hydrogen begins to contract, it needs to cool down to form stars, which it typically does by radiating away heat. However, if a nearby, vigorously forming star or galaxy bathes the cloud in a powerful flood of ultraviolet light, that light can break apart the hydrogen molecules. Atomic hydrogen is a much less efficient coolant than molecular hydrogen. Without this crucial cooling mechanism, the gas cloud cannot fragment into many smaller stars. Instead, it continues to collapse monolithically in a rapid, catastrophic free fall. the entire gigantic cloud, which could be tens of thousands of times more massive than our Sun, plummets inward under its own gravity. The central density and temperature soar to unimaginable levels, and the entire structure buckles directly into a black hole, skipping the star stage entirely. In one single dramatic event, a seed black hole is born with a mass of 10,000, 100,000, or even more solar masses, a ready-made giant. The difference between these two seed models is not just a matter of scale, it's a fundamental divergence in the early universe's story. A stellar remnant seed is like a single, hardy pioneer trying to build a metropolis. It has to attract and consume material slowly and steadily, fighting against the radiation pressure its own feeding produces. A direct collapse seed, on the other hand, is more like an entire city council with a massive construction budget arriving on the scene all at once. Its immense gravitational pull from day one gives it a powerful hold on a vast reservoir of surrounding gas, allowing it to begin its feeding frenzy from a position of overwhelming dominance. This is precisely why the large seed model is so often invoked to explain the quasars we see at the edge of time. A direct collapse black hole starting at, say, 100,000 solar masses has a colossal head start. It can grow at a sustainable rate and still easily reach 1 billion solar masses within the tight time frame the early universe allows. The existence of a black hole like J0313-1806 is therefore a strong piece of circumstantial evidence that such dramatic direct collapse events did indeed occur in the dense, chaotic environments of the cosmic dawn. They were the universe's preferred method for jump-starting the growth of its most massive gravitational engines, setting the stage for the evolution of galaxies and the large-scale structure we see today. The choice of seed, it turns out, dictates the fate of cosmic structures for billions of years to come. This role as a cosmic beacon extends far beyond simply marking a location. These distant quasars fundamentally transformed the universe around them. Their intense radiation did not just travel through the vast emptiness, it actively sculpted it, changing the very nature of cosmic matter during a pivotal era known as the epoch of reionization. For the first several hundred million years after the Big Bang, the universe was a fundamentally different place. It was filled with a dense, opaque fog of neutral hydrogen gas. Neutral hydrogen is simply a proton with an electron bound to it, and these atoms efficiently absorb the high-energy ultraviolet light that stars and quasars emit. This meant the early cosmos was shrouded, a dark age where light could not travel far before being swallowed by the pervasive gloom. But then the first brilliant objects began to switch on. The earliest stars, galaxies, and most powerfully, these incredibly luminous quasars, started flooding the cosmos with an unprecedented torrent of ultraviolet and X-ray radiation. This radiation is so energetic that when it strikes a neutral hydrogen atom, it has the power to rip the electron clean away from the proton in a process called ionization. Think of these quasars as cosmic blowtorches, carving out vast, transparent bubbles in the opaque fog. Their radiation would blast through the neutral hydrogen, stripping atoms bare and creating expanding spheres of ionized, electrically charged plasma, protons and electrons flying freely, no longer able to absorb the light passing through. Over hundreds of millions of years, these individual bubbles grew and overlapped, eventually clearing the fog from the entire universe and making it transparent to light, much as it is today. This was the epoch of reionization, the universe's great unveiling, and the most distant quasars we observe were among the primary architects of this cosmic transformation, their powerful beams helping to end the dark ages and usher in the clear, star-filled universe we now inhabit. Beyond this active role in sculpting the cosmos, these brilliant beacons provide us with an even more direct tool for exploration. As their light journeys for billions of years to reach our telescopes, it does not travel through a perfect vacuum. It passes through the sparse and mostly invisible material that exists between galaxies, the intergalactic medium, a cosmic web of incredibly diffuse gas and dark matter. This is where the quasar truly becomes a lighthouse, its beam illuminating everything in its path. Astronomers use it as a powerful backlight. By carefully dissecting the quasar's spectrum, the detailed fingerprint of its light spread out into a rainbow of colors, they don't just see a smooth, continuous band. They find a Lyman alpha forest, a complex pattern of hundreds of dark absorption lines cutting into the spectrum. Each of these lines is a telltale signature. As the quasar's light travels toward us, it passes through innumerable clouds and filaments of neutral hydrogen that trace the cosmic web. When the light at a very specific wavelength, the wavelength that neutral hydrogen loves to absorb, encounters one of these clouds, it gets snatched out of the beam. This creates a sharp, dark dip in the quasar's spectrum at that particular wavelength. Because the universe is expanding, each cloud is moving away from us at a slightly different speed, which shifts the absorption line to a different position in the spectrum. The result is a veritable barcode of absorption features, with each line corresponding to a different cloud of hydrogen at a different distance along the line of sight. By decoding this intricate barcode, astronomers can perform a kind of cosmic tomography. They can map out the distribution, temperature, and density of this otherwise invisible intergalactic material, reconstructing the large-scale structure of the universe across billions of light years. They can even study the chemical composition of the early cosmos, as the spectra sometimes reveal faint traces of heavier elements like carbon and oxygen, forged in the first generations of stars and then scattered into the void by supernova explosions. So these distant black holes, through the brilliant quasars they power, serve a dual purpose. They are both active sculptors of the cosmic landscape, using their raw energy to clear the primordial fog, and they are also our most powerful flashlights, casting their beams across the universe to reveal the intricate, filamentary structure of everything that lies between them and us. We are not just observing a single point of light. We are using that light to conduct a forensic analysis of the entire cosmic highway it has traveled, uncovering secrets about the universe's structure and history that would otherwise remain forever hidden in the dark. While the brilliant quasars rightfully capture our attention with their staggering luminosity, they represent only one part of the story, the loudest and most flamboyant members of a much broader and more diverse population. For every supermassive black hole in the early universe that was throwing a spectacular, brightly lit feast, there were countless others sitting in the cosmic dark, silent and dormant. These are the quiet giants, the sleeping monsters whose detection presents an entirely different and arguably even greater challenge for astronomers. The very technique that allows us to see the active quasars, their brilliant accretion disks, is useless here. A dormant black hole, by definition, is not actively consuming large amounts of material. Its dinner plate is empty, and without that superheated, glowing accretion disk, it emits virtually no light for our telescopes to catch. It becomes a shadow within a shadow, an invisible gravitational pit hiding in the darkness of a distant young galaxy. So how do you find something that gives off no light? Astronomers have to become cosmic detectives, looking for the subtle, indirect clues that such an object leaves behind. One of the most effective methods is to observe the motion of stars near the center of a distant galaxy. Even if the central black hole is dormant, its immense gravity still dictates the dance of the stars around it. By measuring the velocities of these stars with incredible precision, scientists can detect the telltale signs of a massive, unseen object holding them in its grip. Stars orbiting close to the galactic center will be whipping around at astonishing speeds, their motion betraying the presence of a tremendous mass confined to a very small volume, the classic signature of a supermassive black hole, even a sleeping one. Another method involves looking for the occasional, faint flicker. A dormant black hole isn't completely dead. it might still snack on a passing star or a small cloud of gas every now and then. These minor accretion events can produce brief, low-level flares of X-rays or other radiation, tiny burps that signal the presence of a hidden beast. Catching these fleeting moments requires immense patience and sustained monitoring of thousands of distant galaxies, but each detection adds a crucial piece to the puzzle. Beyond the dormant supermassive black holes, there is an even more elusive group to consider: the smaller stellar mass black holes from the early universe. These are the remnants of the very first massive stars that lived and died explosively. Finding these individual objects at cosmic distances is currently beyond our technological reach, as they are simply too faint. However, their collective presence can be inferred. The eventual mergers of these stellar mass black holes are the source of the gravitational waves we now detect with observatories like LIGO and Virgo. While we cannot yet pinpoint the individual black holes responsible for these ripples in spacetime from the cosmic dawn, each gravitational wave signal we capture is a statistical confirmation that these smaller black holes were indeed forming and merging in the ancient universe. Understanding this full spectrum, from the brilliant quasars to the quiet giants and the small, merging remnants, is absolutely vital for creating a complete census of black hole growth. If we only study the active quasars, we are effectively only taking a census of the population during their brief, flashy eating periods. This would be like trying to understand human eating habits by only observing people at an all-you-can-eat buffet. You get a very skewed picture. The dormant phases are where black holes likely spend the majority of their lives, quietly influencing their host galaxies through gravity alone. By finding these hidden populations, we can answer fundamental questions. What is the true ratio of active to dormant black holes in the early universe? How does a black hole cycle between active feeding and long periods of quiescence? Do all galaxies, even the small, faint ones in the early cosmos, host a central black hole, or was that a privilege reserved for only the most massive systems? Each dormant black hole we identify adds a critical data point, moving us from a story based only on the most extreme examples to a true, nuanced history of how these gravitational anchors shaped the cosmos from its very beginning. One of the most surprising revelations in our study of the universe's most distant black holes concerns the very homes they reside in. For a long time, it seemed logical to assume that a truly colossal black hole, one with a mass of 1 billion suns or more, must sit at the heart of an equally colossal galaxy, a cosmic titan matching a titan. This idea of a predictable hand-in-hand growth known as co-evolution was a cornerstone of our models, but the universe, as it often does, has a way of upending our most reasonable expectations. The latest data, particularly from the revolutionary James Webb Space Telescope, is showing us that the host galaxies of these ancient quasars are far more diverse and, in many cases, far less imposing than we ever predicted. We are finding that in the early universe, a monster black hole did not necessarily require a monster galaxy to host it. The James Webb Space Telescope, with its unprecedented infrared sensitivity, has finally given us the ability to peer through the brilliant glare of the quasar itself and see the faint, underlying structure of its host galaxy. What we are finding is astonishing. Some of these galaxies are indeed massive as expected, but many others are surprisingly compact and chaotic. Imagine a bustling, dense metropolis crammed into an area far smaller than our own Milky Way, yet producing a central gravitational engine that outshines everything around it. These are not the serene, well-ordered spiral galaxies or the featureless elliptical giants we see in the modern universe. Instead, they are turbulent, messy, and undergoing extreme bursts of star formation. They are galaxies in their raw, formative years, still assembling themselves, and their central black holes seem to be growing at a rate that outpaces the growth of the galactic bulge of stars surrounding them. This presents a direct challenge to the traditional model of co-evolution. The classic view suggested that a galaxy and its central black hole grew in lockstep, regulated by a feedback mechanism where the energy from the quasar would eventually blow away gas, quenching both star formation and its own growth. But seeing a billion solar mass black hole inside a relatively modest, compact galaxy suggests a different story. It implies that the black hole can, in certain environments, grow incredibly fast first, potentially becoming the dominant gravitational force in the system before the galaxy itself has had time to mature. This is like finding the foundation and framework for a skyscraper already in place on a plot of land that is still mostly undeveloped. The black hole isn't just a product of its galaxy's maturity. In many cases, it seems to be the leading actor shaping the galaxy's destiny from the very beginning. This diversity in host galaxies forces us to consider a wider range of birthplaces for these early supermassive black holes. Perhaps the most massive, direct collapse seeds formed in the densest, most rapidly collapsing peaks of the cosmic web, regardless of the overall size of the protogalaxy forming around them. A small but incredibly gas-rich and turbulent galaxy could provide the perfect, dense feeding ground for a black hole to rapidly accrete material and achieve a dominant size quickly. The key ingredient may not have been the total mass of the galaxy, but the density and availability of gas in its very center. The James Webb observations are painting a picture of the early universe as a place of great experimentation, where black holes and their host galaxies explored many different pathways to growth, some in harmony, and some in a race where the black hole clearly took an early and overwhelming lead. But the spectacle of a supermassive black hole's feeding frenzy can become even more extreme. Beyond the brilliant glow of the accretion disk, some of these cosmic engines develop structures of almost unimaginable power, colossal, narrow beams of energized matter screaming away from the black hole's poles at velocities approaching the speed of light. These are relativistic jets, and they represent one of the most energetic and dramatic processes in the entire universe. While the accretion disk shines with the heat of infalling material, these jets are a testament to the raw, focused power that a black hole can unleash, channeling its gravitational might not just inward, but also outward in a devastatingly precise manner. The formation of these jets is a complex ballet of physics, centered on the black hole's incredible spin and its powerful magnetic fields. As matter spirals inward through the accretion disk, it doesn't all cross the event horizon. Some of the incoming material, along with immense amounts of energy, can get caught up in the black hole's intensely twisted magnetic field lines. Think of it like a cosmic particle accelerator on a scale we could never hope to build on Earth. The black hole's rapid rotation, combined with these magnetic fields, acts as a slingshot, funneling a fraction of the superheated plasma away from the poles, perpendicular to the disk. This material is accelerated with such violence that it is shot out into the void in two oppositely directed, incredibly narrow beams, often moving at 99.9% the speed of light. Detecting these jets from the edge of the observable universe is a fascinating challenge. While the jets themselves are made of plasma, their interaction with the intergalactic medium and their own internal processes makes them brilliant sources of radio waves. When a jet slams into the thin gas that exists between galaxies, it creates a violent shock wave, causing the particles within to radiate powerfully at radio frequencies. From our perspective on Earth, these distant quasars with active jets often appear as incredibly bright, compact radio sources. In some cases, the jets can be traced for hundreds of thousands of light years, far beyond the confines of their host galaxy, appearing as colossal, luminous lobes on either side of the central engine. These radio lobes are the lingering echoes of the jet's immense power, a fossil record of its long-term activity. The impact of these jets on their cosmic environment cannot be overstated. They are a primary form of black hole feedback. A supermassive black hole may be a powerful eater, but its jets act as a cosmic regulator, preventing it from growing indefinitely and fundamentally shaping the evolution of its entire host galaxy. These beams carry a staggering amount of energy directly into the galaxy's reservoir of cold gas, the very fuel needed for forming new stars. When the jet plows into this gas, it heats it violently, shocks it, and can even blow it completely out of the galaxy. This process effectively shuts down star formation by removing the raw materials, a phenomenon known as quenching. In this way, the black hole, through its own explosive outbursts, can dictate the life cycle of its home galaxy, transforming a vibrant, star-forming factory into a quiet, aging stellar population. The most distant black holes with powerful jets were not just passive residents of the early cosmos. They were active, dominant architects, using these focused beams to carve out their legacy and influence the fate of matter for billions of years to come. Getting an accurate measurement for the mass of a black hole billions of light years away seems like an impossible task, like trying to weigh a mountain from the other side of the planet without ever touching it. Yet, this is precisely the extraordinary feat astronomers accomplish. The key, once again, lies not in observing the black hole itself, but in carefully watching the behavior of the material caught in its ferocious gravitational grip. The most powerful and widely used technique for this cosmic scale weigh-in is a brilliant method known as reverberation mapping. Imagine the entire central region of an active quasar as a complex, multi-layered engine. At the very heart, of course, is the supermassive black hole. Orbiting it at dizzying speeds is the bright, hot accretion disk, the source of the quasar's intense continuous light. Further out, at a distance of perhaps light days or light weeks from the black hole, floats a cloud of dense gas known as the broadline region. This gas is so named because when we look at its spectral signature, the emission lines are extremely wide or broadened. This broadening isn't a visual effect, it's a direct result of the gas's incredible motion. Some clouds are racing directly toward us at thousands of kilometers per second, while others are moving away at similar speeds, all under the influence of the central black hole's gravity. This extreme Doppler shifting smears the sharp spectral line into a broad, fat hump. The principle of reverberation mapping is deceptively simple: light echoes. Think of it as cosmic sonar. The intensely bright accretion disk at the center is not perfectly steady. It flickers and fluctuates in brightness over time. When a flare of increased brightness occurs in the accretion disk, it sends a pulse of high-energy ultraviolet light radiating outward in all directions. This light pulse travels at, well, the speed of light. After a certain amount of time, a delay, that pulse of light reaches the more distant broadline region. The high-energy photons excite the gas clouds in this region, causing them to fluoresce or re-emit light at specific, characteristic wavelengths. We see this as a corresponding flare in the broad emission lines in the quasar spectrum. Crucially, the time delay between the initial flare in the accretion disk's continuum light and the responding flare in the broad emission lines is a direct measure of the distance between the accretion disk and the broadline region. Light travel time provides a cosmic ruler. This single measurement unlocks everything. Once astronomers know the radius of the broadline region from this time delay measurement, they can apply the fundamental laws of orbital mechanics. The gas in the broadline region is in a state of near-chaotic, high-velocity orbit around the central mass. By measuring the width of the broad emission lines, astronomers are directly measuring the velocity of that orbiting gas. The broader the line, the faster the gas is moving. With the radius of the orbit now known from the reverberation delay and the orbital speed known from the line width, Newton's laws, refined by general relativity, provide the final answer. The mass of the central object required to hold that fast-moving gas in an orbit at that specific distance can be calculated with remarkable precision. It's the same basic physics we use to weigh the Sun by measuring Earth's orbital distance and speed. just applied to an environment of unimaginable violence and scale. This technique reveals masses that are truly humbling. For the distant quasar J0313-1806, reverberation mapping and other methods confirmed a central black hole mass of over 1.6 billion solar masses. To hold gas in an orbit light weeks away at speeds of thousands of kilometers per second requires a gravitational anchor of almost incomprehensible power. This method transforms the flickering, chaotic light of a quasar from a mere spectacle into a precise scientific instrument, allowing us to place these cosmic giants on a scale from billions of light years away and truly comprehend the monumental forces at work at the edge of spacetime. When a black hole feeds, it's not a simple, silent process of matter vanishing into the dark. It's a violent, self-regulating drama where the very act of consumption can eventually shut down the supply line. This cosmic balancing act is governed by a fundamental principle in astrophysics known as the Eddington limit. Named for the famed astronomer Arthur Eddington, this limit defines the theoretical maximum rate at which a black hole, or any accreting object, can pull in matter before the intense radiation it produces starts to fight back. Think of it like a cosmic version of trying to eat with a flashlight shining directly into your face. The brighter the light, the harder it is to see and reach the food. For a black hole, the food is the surrounding gas, and the light is the unbelievable outpouring of energy from its superheated accretion disk. As gas spirals inward, it's heated to millions of degrees, emitting a torrent of photons, particles of light. This radiation doesn't just travel outward peacefully, it exerts a tangible force known as radiation pressure. When these photons strike atoms in the infalling gas, they push on them, much like the wind pushes against a sail. The Eddington limit is the precise point at which this outward push of radiation perfectly balances the inward pull of the black hole's gravity. At this equilibrium, the force of light pushing out is strong enough to halt any additional gas from falling in. It's a natural thermostat, a self-imposed speed limit that prevents the black hole from greedily consuming everything at once. For a typical supermassive black hole, sustaining accretion at this maximum rate would still allow for impressive growth, potentially doubling its mass every few tens of millions of years. But when we look at the billion solar mass behemoths existing just a few 100 million years after the Big Bang, even this maximum sustainable rate feels frustratingly slow, like a steady drip trying to fill a colossal bucket in a matter of minutes. This is where the plot thickens, and astrophysicists explore a fascinating loophole, the possibility of super Eddington accretion. This is the theory that, under the right conditions, a black hole can temporarily gorge itself at rates far exceeding its supposed limit. It's the difference between a steady diet and a spectacular, chaotic binge. How is this possible? The key lies in the geometry and density of the inflowing material. The classic Eddington limit calculation assumes a perfectly spherical, steady inflow of gas, but the early universe was anything but neat and orderly. It was a dense, turbulent place where vast, chaotic clouds of gas could collapse directly toward the black hole. In this scenario, the incoming matter might be so thick and dense that the radiation produced by the accretion disk simply cannot escape to push it all away. The photons become trapped, bouncing around within the dense shroud of gas, their energy absorbed and re-radiated, losing their outward momentum. It would be like trying to stop a stampede with a searchlight. The light is bright, but the sheer mass and momentum of the crowd simply overwhelm it. This opens the door for brief, explosive periods of hyperfeeding. Instead of a smooth, thin disk, matter could flood in from all directions in a thick, chaotic flow, allowing the black hole to consume material at rates many times the Eddington limit. This isn't a gentle rain, it's a hurricane of gas. During these super Eddington episodes, the accretion process becomes incredibly inefficient and messy. Much of the gas may not even reach the event horizon, instead being flung away in powerful outflows. But even if a large fraction is lost, the sheer volume of the incoming torrent means the black hole's mass can still skyrocket in a relatively short cosmic timespan. This idea of a duty cycle alternating between brief, violent feasts and long, quiet fasts could be the key to solving the growth paradox. A black hole wouldn't need to feed steadily at its maximum rate for its entire life. It could achieve its colossal size through a series of spectacular, short-lived growth spurts, gorging itself in the uniquely rich environments of the nascent cosmos before its own brilliance temporarily shuts down the buffet. This brilliant, flamboyant phase of a supermassive black hole's life, the spectacular quasar state that makes it visible across the cosmos, is not a permanent condition. It is a fleeting chapter in a much longer story, a temporary blaze of glory in a life cycle that spans billions of years. These cosmic engines can, and often do, effectively shut off, transitioning from a brilliant beacon to a dark and silent sentinel at the heart of its galaxy. The quasar phase is a period of extreme activity, but it is a state that is fundamentally unsustainable over the long term, typically lasting for tens to hundreds of millions of years, a long time by human standards, but merely a brief flash in the multi-billion-year history of a galaxy. This cycle of activity and dormancy is governed by one simple, crucial resource: the availability of fuel. The primary mechanism that shuts down a quasar is the same thing that turns it on: the flow of gas. For the brilliant accretion disk to shine, it requires a steady, dense supply of cold gas to spiral inward. But this fuel reservoir is not infinite, and several cosmic events can disrupt or completely sever this supply line. One of the most dramatic is a galactic merger. When two galaxies collide, it's a chaotic and gravitational upheaval. While it might seem like such an event would funnel vast new amounts of gas toward the central black hole, triggering a spectacular outburst, which it often does initially, the long-term effect can be quite the opposite. The immense gravitational forces during a major merger can slingshot gas out into the far reaches of the newly formed galaxy, or heat it to such extreme temperatures that it becomes too energetic to collapse and feed the black hole. The very event that provides a short-term feast can ultimately lead to a long-term famine, clearing out the central larder and leaving the black hole with nothing left to consume. Perhaps an even more fascinating shutdown mechanism is the black hole's own self-destructive brilliance. This is the concept of feedback, a powerful cosmic regulation system. As we discussed with relativistic jets, the incredible energy pouring out from the quasar doesn't just travel off into space unnoticed. It violently interacts with the very gas that is feeding it. The intense radiation pressure and powerful winds blowing off the accretion disk can push against the incoming clouds of fuel, slowing their descent. In more extreme cases, this feedback can become an outright eruption. The energy output is so colossal that it heats the surrounding galactic gas to millions of degrees, or physically blows it clean out of the galaxy's central regions in a massive outflow. Imagine a fire so intense that it not only consumes its fuel but creates a powerful wind that blows all the remaining wood far away, putting itself out. The black hole, in its most voracious feeding state, effectively triggers a shutdown sequence by destroying its own fuel supply. It gorges itself into a coma, leaving behind a dormant supermassive black hole, a sleeping giant whose immense gravity is still present, but which no longer shines with the telltale brilliance of an active accretion disk. This cycle of activity and quiescence helps explain the incredible diversity we see in galaxies today. Our own Milky Way hosts a supermassive black hole, Sagittarius A, which is a perfect example of a dormant giant. It has a mass of over 4 million suns, yet it is incredibly faint, emitting only tiny trickles of energy compared to its potential. It is a quiet engine, likely because the galactic center has been largely cleared of the dense, cold gas needed to power a significant outburst. We see this pattern across the universe. brilliant quasars in the early, gas-rich cosmos, and a higher proportion of quiet, dormant black holes in the more settled modern universe. This life cycle is crucial to understanding galactic evolution. A black hole's active phase is not just a light show, it's a formative period that directly influences the future of its host. By blowing away gas, it can quench star formation, determining whether a galaxy remains a blue, star-forming spiral or transitions into a red, dead elliptical. The most distant black holes we observe are often caught in the act of this self-regulation, their brilliant light a signature of a dramatic transformation that will ultimately lead to their own silence and shape the cosmic landscape for eons to come. All this talk of distant giants and cosmic dawn leads to a crucial question. How are we making these incredible discoveries, pushing the frontier of observation closer and closer to the Big Bang itself? The answer, in large part, arrives in the form of a technological marvel orbiting 1,000,000 miles from Earth, the James Webb Space Telescope. This observatory isn't just an incremental improvement, it is a paradigm shift, a machine specifically engineered to see the unseeable and to act as our ultimate time machine, peering into an epoch that was previously little more than theoretical. Its revolutionary impact stems from one fundamental design choice. It is a telescope that sees the universe in infrared light. To understand why this is so transformative, we need to remember the effect of cosmic expansion on the light from these incredibly distant objects. The light from the earliest galaxies and quasars, emitted as ultraviolet and visible light, has been traveling for over 13 billion years. During that immense journey, the expanding universe has stretched the very wavelengths of that light, shifting it far into the infrared part of the spectrum. It's like the cosmic equivalent of a siren's pitch dropping as an ambulance speeds away, but applied to light across billions of light years. For previous workhorse telescopes like Hubble, which primarily sees invisible and ultraviolet light, this stretched infrared light from the earliest cosmic objects is largely invisible. It's like trying to listen to a deep bass note with a microphone designed only for high-pitched sounds. The James Webb Space Telescope, however, is that perfect, sensitive microphone for the deep notes of the cosmos. Its giant gold-coated mirrors and sophisticated infrared instruments are chilled to incredibly low temperatures to detect this faint, heat-like radiation with unparalleled clarity, finally pulling back the curtain on the universe's first chapters. And the discoveries are already pouring in, fundamentally reshaping our understanding of the early universe and the black holes within it. Astronomers pointed Webb's powerful gaze at patches of sky that Hubble had stared at for days, revealing what was once empty darkness to be teeming with faint, red smudges galaxies that were completely invisible before. But the real shock came when they analyzed the light from these newfound galaxies. Webb has confirmed the existence of galaxies with redshifts so high they correspond to a time when the universe was only 200 to 300 million years old. That's a mere 2% of its current age, and nestled within many of these infant galaxies, the data reveals the telltale signatures of actively growing black holes. These aren't necessarily the brilliant, obvious quasars we find slightly later in cosmic history. Many are smaller, more obscured black holes caught in the very early stages of their growth. This is a critical discovery because it suggests that supermassive black holes didn't just appear out of nowhere as fully formed giants. They were already relatively common features in the very first galactic structures. Webb is giving us our first true census of black hole formation in the cosmic dawn, showing that the seeds for these future monsters were planted almost immediately after the first stars began to shine. Perhaps the most startling and controversial of Webb's early findings concerns a specific class of objects that appear far too massive and far too evolved for their age. The telescope has identified several galaxies that, based on the brightness and redness of their light, seem to contain hundreds of billions of stars, all when the universe was less than 400 million years old. According to our standard models of galaxy formation, Building such a colossal structure should have taken much longer. The leading explanation for these unexpectedly massive objects is that they are powered by intensely active supermassive black holes. Their incredible luminosity isn't coming from stars alone, but from the ferocious glow of a gargantuan accretion disk at their core, whose light is reddened by vast clouds of dust. If this interpretation holds, it means that black holes were not only present in the earliest galaxies, but in some cases they were already the dominant source of light and energy, outpacing the growth of the stars around them on a staggering scale. These observations are pushing the frontier of the observable universe not just in terms of distance, but in terms of our theoretical understanding. They are forcing us to confront the possibility that the very first black holes could have grown with a speed and efficiency that challenges our most fundamental physics, suggesting that the conditions in the primordial cosmos were even more extreme and conducive to rapid structure formation than we ever dared to imagine. With every new image and spectrum, the James Webb Space Telescope is not just filling in gaps in our knowledge. It is redrawing the map of cosmic dawn, revealing a universe that got off to a far more dynamic and explosive start than we had previously conceived. Beyond simply being cosmic lighthouses or galactic architects, these distant black holes serve a function that is arguably even more profound. They are nature's ultimate laboratories, providing a unique testing ground for the laws of physics under conditions so extreme they could never be recreated on Earth. The environment around a supermassive black hole is a realm of radical extremes, where gravity is so powerful it warps the very fabric of reality. Matter is accelerated to a fraction of the speed of light, and densities reach levels unseen since the first moments of the Big Bang. By observing these far-off giants, we are effectively running experiments on a cosmic scale, probing the fundamental nature of gravity, space-time, and matter itself. One of the most crucial tests involves Einstein's theory of general relativity. For over a century, this theory has passed every experimental challenge thrown at it, from the precise orbit of Mercury to the detection of gravitational waves. But a major question remains: does it still hold true in the most intense gravitational fields imaginable? The region just outside a black hole's event horizon is the ultimate proving ground. Here, gravity is not just a gentle force, it dictates the geometry of the universe, twisting space-time into a vortex around the central singularity. By meticulously studying the light from the accretion disks of these distant quasars, astronomers can search for subtle deviations from Einstein's predictions. For instance, the way light is stretched and lensed by the black hole's immense gravity, or the precise orbital patterns of the hot gas at the inner edge of the accretion disk, could reveal tiny cracks in the framework of general relativity. Finding such a discrepancy wouldn't invalidate Einstein's work, but it would point the way toward a more complete theory, one that could potentially unite gravity with quantum mechanics, the holy grail of modern physics. These black holes are the only places in the universe where gravity is strong enough to conduct such a test. Furthermore, these objects allow us to explore the very properties of spacetime. The concept of frame dragging, where a massive, rotating object literally pulls the fabric of spacetime around with it, is predicted by general relativity. While this effect has been measured around Earth, it is minuscule. Around a rapidly spinning supermassive black hole, however, frame dragging becomes a dominant force, creating a whirlpool in spacetime that can dramatically influence the motion of the entire accretion disk and the formation of its powerful jets. By analyzing the properties of the light and the jet structures from these distant quasars, we can infer the spin of the central black hole, giving us direct insight into this dramatic warping of the cosmos. It's like being able to study the properties of a whirlpool by observing how it affects floating leaves, but on a scale that encompasses entire solar systems. These natural laboratories also offer us a rare window into the behavior of matter at its absolute limit. The density and pressure inside a black hole's accretion disk or within the plasma of its relativistic jets are states of matter that we cannot replicate in any particle accelerator on Earth. The conditions are so extreme that they push atomic nuclei to their breaking point, creating a superheated plasma where the rules of nuclear physics and magnetohydrodynamics intertwine in complex ways. By studying the X-ray and gamma-ray emissions from these regions, we learn about how matter behaves when it is not just hot, but when it is dominated by unimaginable gravitational and magnetic forces. This isn't just abstract knowledge, it helps us understand the fundamental processes that govern how energy is extracted from black holes, how jets are launched and collimated, and how elements are forged and scattered throughout the universe in these cosmic cauldrons. Ultimately, observing the most distant black holes is the closest we can get to experimentally studying the conditions of the very early universe. The incredible density and temperature of the primordial cosmos, just moments after the Big Bang, are echoed in the violent environments surrounding these ancient objects. They preserve a record of a time when the universe was smaller, hotter, and far more energetic. By understanding the physics at work around a black hole from when the universe was only a few 100 million years old, we gain indirect insight into the physical laws that govern the entire cosmos during its infancy. Each photon that arrives from one of these distant quasars carries not just information about the black hole itself, but encoded data about the fundamental constants of nature and the validity of our physical theories across billions of years of cosmic evolution. They are not merely objects in space, they are active, dynamic experiments, gifting us with data from the most extreme frontier of reality, data that continues to challenge and refine our understanding of the universe's most basic rules. Stepping back from the individual discoveries, we arrive at one of the most profound and unresolved mysteries in all of cosmology, the nature of the absolute first black hole. What did that inaugural singularity look like, the one that broke the pristine silence of the early cosmos and set in motion the chain of events that would lead to the billion solar mass giants we find just a few 100 million years later? While we may never pinpoint that single specific object, we can use the laws of physics and our observations of the distant universe to speculate on its likely origins, and in doing so, we are led directly to the hunt for the most elusive stars in existence. The prevailing theory points to a specific hypothetical class of stars known as population 3. Our own Sun is a population 1 star, rich in heavier elements like carbon, oxygen, and iron, the ashes of countless generations of stellar explosions that came before it. The very first stars could not have been like this. They formed from the primordial soup left by the Big Bang, a universe composed of roughly 75% hydrogen and 25% helium, with no heavier elements whatsoever. This pure composition had a dramatic effect on their life cycle. In modern star formation, elements like carbon and oxygen act as a coolant, allowing a gas cloud to fragment into many stars of various sizes, including small, long-lived stars like our Sun. But without these cooling agents, the primordial gas clouds could not efficiently shed their heat as they collapsed. This led to a much hotter, more monolithic collapse, resulting in stars that were, by all estimates, true behemoths. We are talking about stars that could have been hundreds, even thousands, of times more massive than our own Sun. The life of a population 3 star would have been spectacularly brief and violent. Burning their nuclear fuel at a ferocious rate to support their immense weight against gravity, they would have lived for only a few million years, a cosmic blink of an eye. Their deaths, however, would have been anything but quiet. For the most massive of these giants, their end would have been a cataclysm known as a pair instability supernova, an explosion so powerful that it would have completely annihilated the star, leaving nothing behind, not even a black hole, and scattering the first heavy elements across the cosmos. But for those stars in a specific mass range, perhaps between about 60 and a few hundred solar masses, the core collapse would have been so swift and total that the entire star would have imploded directly, bypassing a significant supernova explosion and collapsing straight into a black hole. This, then, is the most widely accepted candidate for the universe's first black holes, the stellar mass remnants of the very first impossibly massive stars. The search for these population 3 stars and their black hole remnants is one of astronomy's great holy grails. They are the missing link, the progenitors that planted the initial seeds for all subsequent supermassive black hole growth. Finding direct evidence of them, however, is incredibly difficult. Their lives were so short that they flickered out long ago, and their pure composition means their light would have had a very distinct spectral signature that we have yet to definitively identify. The James Webb Space Telescope is our best hope for finally catching a glimpse of them. By staring deeply at the most distant redshifted galaxies, astronomers are searching for the unique chemical fingerprints of a system that has been enriched by only a single generation of stars, a telltale abundance pattern that would point to a recent population 3 supernova. Alternatively, we might catch the indirect echo of their deaths through gravitational waves. The mergers of these first-generation stellar mass black holes would have sent ripples through spacetime, and while current observatories like LIGO might not be able to pinpoint them to that specific epoch, future space-based detectors could one day listen for the faint whispers of these primordial collisions. Yet the story might be even more exotic. Another compelling theory suggests that the very first black holes weren't stellar in origin at all, but were instead forged in the incredible density and temperature of the Big Bang itself. These would be primordial black holes created not from dying stars, but from the gravitational collapse of extreme density fluctuations in the first moments of the universe. If they existed with the right mass range, they could have served as ready-made seeds scattered throughout the cosmos from day one, providing a head start for the growth of supermassive black holes. The nature of that very first black hole, therefore, is more than just a historical curiosity. It is the foundational question that determines which growth story for the distant quasars we've discussed is even possible. Did everything begin with the dramatic death of a colossal star, or was the universe born with its gravitational anchors already in place? The answer lies hidden in the faintest light from the cosmic dawn, waiting for our next generation of telescopes to finally reveal it. Now, having explored how we find and weigh these distant giants, we need to step into the realm of the truly mind-bending, to the very heart of what makes a black hole a black hole. It's not just an object of immense mass, it is a profound distortion in the fabric of reality itself. To understand this, we have to move beyond thinking of space as a static, empty stage where events simply play out. Instead, thanks to Einstein, we understand that space and time are woven together into a single, dynamic fabric called space-time. And mass, especially immense mass, doesn't just sit in this fabric, it warps it, curves it, and reshapes it. A classic and helpful way to picture this is to imagine space-time as a vast, perfectly taut, elastic rubber sheet. If you place a small, lightweight object like a marble on that sheet, it creates a very tiny, almost imperceptible dimple. This is similar to how the Earth's gravity creates a gentle curvature in space-time around it. Now, replace that marble with an incredibly heavy bowling ball. The bowling ball sinks deep into the sheet, creating a steep, funnel-like depression around it. A supermassive black hole is the ultimate cosmic bowling ball. Its mass is so concentrated, so overwhelming, that it doesn't just make a dimple, it punches a deep, bottomless well into the rubber sheet of space-time. This curvature is gravity. Objects don't fall toward a black hole because of some mysterious, invisible force pulling them. They simply follow the natural contours of the warped space-time around it. It's like a rolling bead on that rubber sheet. It will naturally spiral inward toward the bowling ball, following the curve that the mass has created. This warping of space-time isn't just a theoretical idea. It has direct, observable consequences that we can detect from billions of light years away. One of the most stunning is the phenomenon of gravitational lensing, which we touched on earlier. When light from a distant quasar travels toward us, it must pass through the curved space-time surrounding a massive foreground object like a galaxy cluster. The light doesn't travel in a straight line as we'd expect in flat space. Instead, it follows the bends and curves of the warped fabric. From our perspective, this bends the light's path, distorting and magnifying the image of the background quasar, sometimes even smearing it into brilliant arcs or creating multiple images of the same single object. It's a direct visual confirmation that the mass of the foreground cluster is physically bending the space through which the light travels, acting as a cosmic lens. But the warping goes even deeper than the path of light. It fundamentally warps time itself in a process called gravitational time dilation. Imagine two incredibly brave astronauts. One stays in a safe, distant orbit, while the other, against all better judgment, decides to descend very close to the black hole's event horizon. The orbiting astronaut is in a region of weaker spacetime curvature, while the daring explorer is in a region of extreme curvature. According to Einstein's equations, time itself flows at different rates in these different gravitational environments. For the astronaut near the event horizon, time would appear to pass perfectly normally. Their watch would tick second by second, and they would feel nothing unusual. However, from the perspective of the distant astronaut watching through a powerful telescope, something bizarre would happen. The closer their companion got to the event horizon, the more their movements would appear to slow down, as if watching a video in extreme slow motion. The light coming from them would become increasingly redshifted, fading into longer and longer wavelengths. If the descending astronaut could hover just at the brink of the event horizon from the outside perspective, their time would appear to grind to a complete halt. They would be frozen in place for all eternity, never quite seen to cross the threshold, their image perpetually stretched and dimmed. This isn't an illusion or a trick of light, it is a fundamental property of spacetime. The immense gravity of the black hole stretches the very dimension of time, creating a gradient where clocks tick slower the deeper into the gravitational well you go. This extreme curvature is also what creates the black hole's most defining feature, the event horizon. This is not a physical surface you could touch, it is a mathematical boundary, the point of no return. It's the specific distance from the singularity where the curvature of spacetime becomes so severe that the path of anything trying to escape, even light itself, bends completely back in on itself. Think of it as the edge of the waterfall. Once you go over the edge, every possible path leads inexorably downward. There are no trajectories that lead back out. For the distant observer, the event horizon is the ultimate cosmic curtain, hiding the final fate of anything that falls within from our view forever. The warping of spacetime by these distant, ancient black holes is therefore not just an abstract concept. It is the engine of their most dramatic effects, from the cosmic mirages of lensing to the profound manipulation of time itself, demonstrating that gravity is the master architect of the cosmos, sculpting both space and the flow of time with its invisible hand. So far, we've explored these distant black holes as incredibly luminous beacons, as cosmic time capsules, and as extreme physics laboratories. But to truly grasp their significance, we need to zoom out to the grandest scale and see them not just as isolated objects, but as fundamental architects of the cosmic web itself. Their influence extends far beyond their own event horizons, actively shaping the evolution of galaxies and the distribution of matter throughout the universe in a continuous process known as cosmic feedback. This isn't a gentle suggestion, it's a powerful regulatory system where a black hole's incredible output can dictate the very life cycle of its galactic home. The most dramatic form of this feedback is delivered by the relativistic jets we discussed earlier. Picture a supermassive black hole in its active quasar phase, not only shining with the brilliance of its accretion disk, but also firing off two pencil-thin beams of energized particles at nearly the speed of light. These jets act as cosmic blowtorches, plowing directly into the heart of the galaxy's star-forming reservoirs, the vast, cold clouds of molecular gas that are the raw material for new stars. When this jet of ultra-fast particles smashes into the relatively placid gas, it creates a violent shock wave, heating the gas to millions of degrees in an instant. This is a transformative event. For a cloud of cold gas to collapse under its own gravity and form stars, it needs to be able to cool down and condense. But gas that has been heated to such extreme temperatures becomes energetically puffed up. Its particles move too fast to clump together. The jet effectively sterilizes the gas, preventing it from ever forming stars. In some of the most extreme outbursts, the energy is so colossal that it doesn't just heat the gas. It physically blows it clean out of the galaxy altogether in a massive galactic-scale wind. This process, known as quenching, can permanently shut down a galaxy's star-forming factory, transforming it from a vibrant blue star-birthing spiral into a quiet, red and aging elliptical galaxy. The black hole, through its own explosive tantrum, dictates the future evolution of its entire host, demonstrating a form of cosmic self-regulation where the central engine prevents its own growth from spiraling out of control by destroying its fuel supply. But the influence of these active black holes doesn't stop at the boundaries of their own galaxies. Their powerful radiation and winds push out into the vast spaces between galaxies, the intergalactic medium. This is the thin, diffuse gas that filaments the cosmic web, and it is the primary reservoir of material for future galaxy formation. When the intense ultraviolet and X-ray radiation from a distant quasar streams through this intergalactic gas, it performs a crucial function. It keeps it hot. By maintaining the high temperature of this gas, the black hole makes it more difficult for it to cool, collapse, and flow into neighboring protogalaxies to fuel their own growth and star formation. It's as if these quasars are acting as cosmic gatekeepers, regulating the flow of raw materials on a regional scale. Furthermore, the heavy elements forged in the hearts of stars and scattered by supernova can be carried along with these quasar-driven winds, chemically enriching the pristine intergalactic medium far from their origin points. This pollution, while making the gas less pure, also seeds the universe with the necessary ingredients for future generations of stars, planets, and potentially life. The black hole's activity becomes a mixing mechanism, ensuring that the building blocks of complexity are distributed throughout the cosmos. This grand interplay between black hole feedback and galaxy evolution has profound implications for the large-scale structure of the universe we see today. The cosmic web, that magnificent filamentary structure of galaxies and clusters surrounded by vast voids, did not form solely through the passive pull of gravity. The energetic input from supermassive black holes played a critical role in sculpting it. In the densest regions of the web, where galaxies cluster together, the feedback from powerful quasars could have heated the surrounding gas so effectively that it prevented smaller satellite galaxies from accreting new cold gas, stunting their growth and influencing the final distribution of galaxies within the cluster. This feedback helps explain why we don't see as many small, faint galaxies as some models of dark matter alone would predict. The baryonic or normal matter was heated and pushed around by these cosmic engines. The most distant black holes were therefore not passive residents of the early cosmos. They were active and dominant participants in the construction of the universe. Their outbursts determined where and when galaxies could form, how large they could grow, and what their ultimate fate would be. They transferred energy from the smallest scales of their event horizons out to the largest scales of the cosmic web. weaving a story of creation and destruction where the most powerful gravitational sinks in existence became the unlikely sculptors of the luminous universe we observe all around us. The hunt for the origins of the universe's first black hole seeds is a cosmic detective story, and one of the most intriguing clues comes from a specific type of stellar death so violent it leaves nothing behind. This is the pair instability supernova, a theoretical explosion that represents nature's ultimate self-destruct mechanism for the most massive stars. To understand how this works, picture a colossal population 3 star, one of the very first, born from pure hydrogen and helium. If such a star falls within a specific mass range, theorized to be between approximately 140 and 260 times the mass of our Sun, its core becomes an unimaginably hot and dense furnace. At these extreme temperatures, the radiation zipping around inside the core is so energetic that it spontaneously transforms from pure light into pairs of particles and their antimatter counterparts, electrons and positrons. This transformation, the birth of matter from light, is a direct consequence of Einstein's famous equation, E equals mc squared. But this beautiful bit of physics has a catastrophic consequence for the star. This process, called pair production, effectively steals the star's energy. The radiation pressure that was fighting to hold the star up against its own immense gravity suddenly drops. Without that outward push, the core can no longer support itself. It begins to collapse inward at a ferocious rate. However, this is not a gentle, steady collapse. As the core contracts, it heats up even further, eventually reaching a temperature where oxygen ignites in an uncontrolled, runaway thermonuclear explosion. This isn't a typical supernova, it's a bomb detonating at the star's very heart. The energy released is so titanic that it doesn't just blow off the star's outer layers, it completely and utterly obliterates the entire stellar structure. The explosion is so thorough that no black hole is left behind, not even a neutron star. The star is entirely vaporized, its ashes scattered into the cosmos, enriching the early universe with the first heavy elements. A pair instability supernova is therefore a cosmic dead end in the story of black hole formation. If a star is massive enough to undergo this process, it cannot possibly become the seed for a future supermassive black hole. This leads to a fascinating and crucial line of inquiry for astronomers. If we can find definitive evidence that pair instability supernova were common in the early universe, it would effectively rule out a huge portion of the most massive primordial stars as potential black hole progenitors. The hunt, then, is for the unique chemical fingerprint of such an event. When a pair instability supernova tears a star apart, it forges and spews out enormous quantities of specific elements in a very distinct pattern. Unlike the supernova from smaller stars that leave behind dense remnants, pair instability events are predicted to produce a tremendous amount of radioactive nickel, which powers the explosion's brightness, and they leave a very specific chemical signature in their ejected material. They are expected to be exceptionally bright and to have a peculiar abundance of elements, with very little mixing of material from the star's deep interior. Finding the ghost of one of these explosions in the light spectrum of an extremely distant, ancient galaxy would be a monumental discovery. The James Webb Space Telescope is now on the front lines of this search. By analyzing the light from the most distant quasars and their surrounding gas, astronomers can detect the faint absorption lines imprinted by the enriched material from early supernova. They are looking for that specific chemical barcode that screams pair instability. Furthermore, wide-field surveys that monitor the sky for transient flashes of light are on the lookout for a supernova with the exact brightness, duration, and color evolution predicted for these ultimate stellar explosions. Finding even a handful of confirmed pair instability supernova in the early universe would profoundly reshape our understanding of black hole seeds. It would tell us that the most massive stars of cosmic dawn effectively committed stellar suicide, erasing themselves from existence and forcing the universe to rely on other, more exotic mechanisms, like the direct collapse of gas clouds, to build the gravitational anchors for its first galaxies. The absence of their chemical signature, on the other hand, would suggest that the conditions for these explosions were rare, leaving the door open for massive stellar corpses to serve as the seeds for the giants we find just a few 100 million years later. This brings us to a crucial point that often gets lost in the grandeur of these ancient objects. Despite their profound age, they are not infinitely old. No black hole in the observable universe is as old as the universe itself. Every single one, from the smallest stellar remnant to the most distant supermassive Leviathan, has a definitive birthday that occurred sometime after the cosmic dawn. To truly appreciate their place in history, we need to rewind the cosmic clock and walk through the formative moments that had to unfold before the first black hole could even be born. The story begins, of course, with the Big Bang, an event that marks time zero, the origin of space, time, matter, and energy itself. For the first fleeting instance, the universe was an undifferentiated, searingly hot and dense soup of fundamental particles. There were no atoms, no stars, and certainly no black holes. The cosmos was simply too hot and too uniform for any structures to hold together against the incredible outward pressure. As the universe expanded and cooled over the first several 100,000 years, a major milestone was reached. Electrons combined with protons to form the first stable atoms, primarily hydrogen and helium. This moment, known as recombination, cleared the cosmic fog and allowed light to travel freely for the first time, a relic we now observe as the cosmic microwave background. But even then, the universe was a profoundly dark and quiet place. It was a featureless sea of gas with no sources of light, no galaxies, and no stars. This period is aptly named the Cosmic Dark Ages. It was within this vast, dark expanse that the first seeds of structure began to sprout. Tiny quantum fluctuations from the Big Bang, magnified by cosmic inflation, created minuscule variations in the density of the primordial gas. Over millions of years, gravity got to work, patiently pulling more and more material toward these slightly denser spots. Eventually, these collapsing clouds of hydrogen and helium became dense and hot enough at their cores to ignite the fire of nuclear fusion. And with that, the very first stars blinked into existence, ending the Dark Ages and igniting the cosmic dawn. This entire process, from the Big Bang to the formation of the first stars, took time anywhere from 100 to a few 100 million years. This is a critical delay. It establishes an absolute lower limit on the age of any black hole. The very first black hole could not possibly have existed before the first star lived out its life and died, because those first stars are what provided the raw material for the first stellar mass black holes. So, when we talk about a black hole from when the universe was only 670 million years old, we are looking at an object that is, cosmically speaking, a first-generation entity. It is a member of one of the earliest possible cohorts of black holes. Its existence tells us that the transition from the first stars to the first gravitational anchors happened with breathtaking speed. The timeline is staggeringly short. A massive star forms, it burns through its nuclear fuel in a frantic few million years, and then it collapses. For the most massive of these pioneers, the collapse was direct and total, creating a black hole in a cosmic instant. The universe went from a dark, starless void to hosting black holes in what amounts to a geological blink of an eye on the cosmic scale. This compressed timeline is precisely what makes their immense sizes so puzzling and forces us to consider those exotic formation mechanisms like direct collapse. They had to form and grow to impossible sizes within a window of time that feels impossibly narrow from our modern perspective, a testament to the violent and dynamic nature of the cosmos in its youth. This brings us to one of the most profound and mind-bending puzzles in all of physics, a conflict so fundamental that its resolution could rewrite our understanding of reality. It's known as the black hole information paradox, and when we apply it to these ancient leviathans from the cosmic dawn, the stakes become even higher. At its heart, this paradox is a direct clash between the two great pillars of modern physics: Einstein's theory of general relativity, which governs the very large and the force of gravity, and quantum mechanics, which governs the very small and the behavior of particles. Both are spectacularly successful in their own domains, but they appear to offer completely contradictory answers to a simple question: what happens to information that falls into a black hole? Let's break this down. In the world of quantum mechanics, there is a sacred principle: information cannot be truly destroyed. It can be scrambled, transformed, or hidden, but it must be preserved in some form. Think of burning a book. The pages turn to ash and smoke, but in principle, if you could collect every single atom and photon and trace their paths with infinite precision, you could theoretically reconstruct the original text. The information about the words on the page still exists in the universe. It's just incredibly difficult to recover. Now, enter a black hole as described by classical general relativity. According to Einstein's theory, a black hole is defined only by its mass, electric charge, and spin. It has no other features, no hair, as physicists colorfully say. If you throw a grand piano, a library of encyclopedias, or 1,000,000 tons of confetti into a black hole, from the outside perspective, all that matters is that the black hole's mass has increased slightly. The specific, intricate information about what you threw in, the composition of the piano, the words in the books, seems to be completely and irrevocably erased from our universe. It's as if the book isn't just burned, the very concept of its information is deleted from existence, violating the core tenet of quantum mechanics. The plot thickened with Stephen Hawking's revolutionary discovery. He showed that black holes are not entirely black. Due to weird quantum effects happening just outside the event horizon, they slowly emit a faint glow of particles, now called Hawking radiation. This radiation causes the black hole to gradually lose mass and, over astronomical timescales, completely evaporate, vanishing from the universe. And here's the crux of the paradox: Hawking's original calculations suggested that this emitted radiation is completely random, purely thermal noise. It carries no information whatsoever about what fell into the black hole. So, if the black hole evaporates away, leaving behind nothing but this featureless thermal radiation, where did the information go? The piano, the encyclopedias, the confetti, the information about them seems to have been utterly destroyed, leaving physicists with a disturbing either-or choice. Either general relativity is wrong about the nature of black holes, or quantum mechanics is wrong about the preservation of information. Now, let's project this cosmic conundrum back in time, to the environment of the most distant black holes. Why would studying these primitive giants offer any special insight? The early universe was a much simpler, more extreme place. It was hotter, denser, and lacked the complex chemical elements that clutter our modern cosmos. The first black holes formed in this pristine environment, potentially from the direct collapse of pure hydrogen and helium clouds. This simplicity is a physicist's dream. There are fewer variables, less contamination from later galactic processes, and a clearer signal of the fundamental physics at play. By studying the properties of these ancient black holes, their mass, spin, and the remnants of their eventual evaporation, if we could detect such a thing, we might be able to see a cleaner version of how information behaves under the most extreme gravitational conditions. One compelling line of thought suggests that the key to the paradox lies not in the black hole's final moments, but in its earliest ones. The way a black hole forms might imprint itself on its subsequent evaporation. For a modern black hole born from a complex supernova, that initial imprint is buried under layers of later infalling material. But for a primordial direct collapse black hole, the initial conditions were far more direct and dramatic. The quantum information of the collapsing gas cloud itself could be processed and preserved in a way that is more apparent in its Hawking radiation. Furthermore, the incredible density of the early universe might have allowed for phenomena we never see today. Perhaps the first black holes were connected by quantum threads known as Einstein-Rosen bridges or wormholes to other regions of spacetime, providing a hidden pathway for information to escape. Or maybe the holographic principle, the idea that all the information within a volume of space can be encoded on its boundary, was more directly manifest in these infant cosmos conditions. The event horizons of the first black holes could have acted like a cosmic film, preserving a two-dimensional holographic imprint of everything that fell in, with that information slowly leaking back out encoded in the Hawking radiation. Observing the most distant quasars and their environments won't solve the paradox outright, but it provides a unique testing ground. It allows us to ask the question in its purest form, in a universe that was still writing its own rules, potentially offering clues that are washed away by 13 billion years of cosmic evolution in our local, modern neighborhood. The silent, ancient light from these objects may carry not just the story of their own formation, but faint hints about the deepest reconciliation of gravity and quantum theory. This brings us to a remarkable property of these cosmic giants that acts like a hidden diary, encoding the story of their violent lives, their spin. Just like a spinning ice skater pulls their arms in to rotate faster, a black hole can possess an incredible amount of rotational energy, and this spin is not just a trivial detail. It is a fossil record, a direct imprint of how the black hole accumulated its mass over billions of years. The rate at which a black hole spins tells us whether it grew through a long, steady diet or a series of dramatic, chaotic mergers. To understand how, we need to look at the very edge of the abyss, at a region governed by one of general relativity's most fascinating predictions, the ergosphere. This is a vast, flattened region of space outside the event horizon of a spinning black hole, where the black hole's rotation is so powerful that it literally drags the fabric of spacetime around with it. Nothing within the ergosphere can remain stationary. Everything is forced to move in the direction of the black hole's spin, caught in a cosmic whirlpool from which not even light can escape. It is within this region of twisted spacetime that the black hole's rotational energy becomes available, potentially powering its relativistic jets and leaving a unique signature on the very light it emits. So, how do you measure the spin of an invisible object billions of light years away? Astronomers perform this incredible feat by carefully analyzing the X-ray light streaming from the superheated material in the black hole's inner accretion disk. As matter spirals inward at velocities approaching the speed of light, it is heated to millions of degrees, emitting a torrent of high-energy X-rays. For a non-spinning black hole, the inner edge of this disk is thought to be relatively far from the event horizon. But for a black hole with rapid spin, the effect is dramatic. The immense rotational energy pulls spacetime itself inward, allowing the accretion disk to extend much closer to the event horizon. This proximity to the point of no return has a direct and measurable effect on the X-ray light. The photons emitted from this innermost region are subjected to an extreme gravitational redshift. Their wavelengths are stretched and their energies reduced as they fight to climb out of the black hole's immense gravity well. Furthermore, the light becomes severely distorted by gravitational lensing effects. By constructing a detailed model of the X-ray spectrum and looking for the specific distortions and energy shifts that only a rapidly spinning black hole can produce, astronomers can essentially map the inner edge of the accretion disk. The closer that inner edge is to the event horizon, the faster the black hole must be spinning. It's a cosmic forensics technique, using the screams of dying matter to read the rotational speed of the gravitational monster consuming it. The story this spin tells is one of two very different paths to becoming a supermassive giant. Consider a black hole that has grown primarily through steady, ordered accretion from a vast gaseous disk over millions of years. As this material spirals inward, it naturally tends to fall into orbits that align with the black hole's existing rotation, like water flowing down a drain. With each new parcel of gas that crosses the event horizon, it brings with it a specific amount of angular momentum, effectively giving the black hole a gentle, continuous push in the same direction. This process, known as coherent accretion, is incredibly efficient at spinning up a black hole. Over time, it can accelerate the black hole to a significant fraction of the maximum spin rate allowed by physics. A rapidly spinning black hole, therefore, is the signature of a relatively peaceful and orderly upbringing, a long, luxurious feast where the food was served consistently and from the same direction. Now imagine a much more violent and chaotic childhood. In the crowded environments of the early universe, galaxy mergers were commonplace, and with them came the mergers of their central supermassive black holes. When two black holes circle each other and finally collide, their individual spins and the complex dynamics of their in-spiral dictate the spin of the final merged object. This is not a neat and tidy process. If the two black holes have spins that are misaligned pointing in different directions, the resulting merger can actually slow down the final black hole, robbing it of rotational energy. It's the cosmic equivalent of trying to spin a merry-go-round by pushing on it from random, conflicting angles. You end up with a lot of jerky, inefficient motion rather than a smooth, fast rotation. A black hole with a slow or moderate spin, therefore, likely has a history written in chaos. It suggests a growth dominated by a series of dramatic mergers, where it grew by cannibalizing its peers in violent, gravitational encounters that randomly tossed and tilted its axis of rotation. By measuring the spin of the ancient black holes at the edge of time, we can begin to distinguish between these two narratives, learning whether the first supermassive black holes built themselves through steady feasting or a storm of celestial violence. But the story of light around these distant giants gets even more intriguing, moving beyond the direct glow of their accretion disks into the realm of cosmic echoes. Imagine standing in a vast, dark cathedral and clapping your hands just once. First, you hear the direct sound. Then, a moment later, you hear a faint echo bouncing back from a distant wall, followed by another, even fainter echo from a pillar further away. Each echo arrives at your ears at a slightly different time, telling you not just that the walls exist, but precisely how far away they are and what they are made of. Now replace the clap with a brilliant flash of light from a black hole's accretion disk, and replace the cathedral walls with vast, swirling clouds of gas in the distant host galaxy. This is the breathtaking phenomenon of a light echo, and it provides astronomers with a powerful tool to conduct cosmic cartography on a scale of billions of light years. The process begins with a sudden, violent eruption on the black hole's doorstep. The accretion disk is not a perfectly steady source of light. It is a turbulent, chaotic environment that can experience dramatic flares. A massive clump of gas might finally spiral inward and be torn apart, or magnetic field lines might snap and reconnect, releasing an incredible burst of energy. This creates a brilliant, short-lived flash of light, primarily high-energy X-rays and ultraviolet radiation, that explodes outward from the central engine in all directions like a cosmic flashbulb. This initial pulse of light is what we see directly, the first clap in our cosmic cathedral. But the story doesn't end there. This flash of light travels outward at, well, the speed of light. After a certain amount of time, it reaches enormous, cold clouds of gas and dust that are floating in the galactic core, light weeks or even light months away from the black hole itself. When the high-energy photons from the flare slam into these clouds, they don't just pass through, they are absorbed by the gas atoms, which then re-emit the energy or reflect it in all directions. From our distant vantage point on Earth, we see this as a delayed brightening of the gas cloud. A cloud that was once faint and invisible suddenly lights up, becoming a temporary, secondary source of light. The true magic and the real scientific value lies in the timing of these echoes. Because light has a finite speed, the echo from a gas cloud that is 10 light days away from the black hole will reach us 10 days after we see the initial flare from the accretion disk. An echo from a cloud 30 light days away will arrive 30 days later. It's a staggered light show, a cascade of illumination that unfolds over weeks or months. By patiently monitoring a distant quasar and carefully measuring the time delay between the initial X-ray flare and the subsequent brightening of different regions in its host galaxy, astronomers can perform a feat of celestial triangulation. They can literally map the three-dimensional structure of the galactic core. Each time delay gives a precise distance, telling us how far a specific gas cloud is from the central black hole. Over time, by catching multiple flares and their resulting echoes, a detailed architectural blueprint of the innermost region of the galaxy emerges. We can see vast, swirling reservoirs of cold molecular gas, the fuel for future star formation. We can identify immense, expanding bubbles of hot gas that have been blown out by the black hole's powerful winds. We can even trace the intricate, spiraling streams of material that are slowly feeding the monster at the center. This technique of echo mapping is incredibly powerful because it allows us to see structure that is otherwise completely hidden. The galactic core of a distant quasar is an incredibly crowded and confusing place. The blinding glare of the accretion disk often washes out the faint light of the surrounding stars and gas, making it impossible to distinguish details with a direct image. It would be like trying to see the details of a mosquito flying in front of a brilliant searchlight. Light echoes cut through this problem. They use the black hole's own violent outbursts against it, turning its flash into our probe. The echoing gas clouds are not competing with the quasar's brightness. They are being selectively illuminated by it, highlighted against the dark backdrop of space. This allows us to study the distribution and composition of the interstellar medium in these infant galaxies with a clarity that was once thought impossible. By analyzing the specific colors or spectrum of the echoed light, we can determine what these distant clouds are made of, their chemical composition, their temperature, and even their density. Every flare from a distant black hole sends out a pulse that not only reveals its own turbulent nature, but also illuminates its immediate surroundings, allowing us to map the hidden architecture of a galaxy's heart from an almost unimaginable distance across both space and time. As breathtaking as the current view from the James Webb Space Telescope may be, we are truly on the cusp of an even more profound observational revolution. The next generation of astronomical observatories, already in advanced stages of planning and construction, promises to not just sharpen our image of the cosmic dawn, but to fundamentally change the way we perceive it, moving from taking snapshots to creating a dynamic, multi-messenger movie of the early universe. These future instruments are not merely incremental upgrades. They are specialized tools designed to tackle the specific, lingering mysteries that our current telescopes have revealed but cannot fully resolve. They will work in concert like a team of expert detectives, each bringing a unique skill set to the investigation of the universe's first black holes. First, consider the power of a sweeping, panoramic view. While the James Webb Space Telescope is a powerful deep-field microscope peering intently at tiny patches of sky, the Nancy Grace Roman Space Telescope will be its wide-angle companion. Scheduled for launch in the latter half of this decade, Roman is designed to be a survey machine of unprecedented speed and scope. Its primary mission involves performing a colossal census of the cosmos, imaging vast swaths of the sky hundreds of times faster than Hubble could. For the hunt for distant black holes, this is a game changer. Instead of painstakingly studying one small area at a time, Roman will scan the heavens, identifying millions of active galactic nuclei and quasars across cosmic time. It will find the rare, extremely high redshift quasars that are currently like finding a needle in a haystack, providing a statistically powerful sample that tells us just how common these early monsters really were. More importantly, its wide-field infrared eyes will catch these objects in the act of flickering. By monitoring the brightness of millions of quasars over time, Roman can perform reverberation mapping on an industrial scale, efficiently measuring black hole masses for tens of thousands of systems, thereby painting a definitive picture of black hole growth and demography from the universe's infancy to the present day. It will provide the broad context, the cosmic map that tells us where to point our most powerful magnifying glasses. And when it comes to magnification, the future holds something almost unimaginably powerful. Here on the ground, in the high, dry deserts of Chile, a behemoth is taking shape, the European Extremely Large Telescope, or ELT, with a primary mirror stretching an astonishing 39 meters across. A mosaic of nearly 800 individual segments, this ground-based titan will gather more than 10 times the light of the largest optical telescopes operating today. Its resolution, aided by sophisticated adaptive optics systems that cancel out the blurring effects of Earth's atmosphere, will be so sharp that it could theoretically distinguish between the headlights of a car on the moon. For studying the host galaxies of the most distant quasars, this is a transformative capability. Where Webb can see the faint smudge of a galaxy around a brilliant quasar, the ELT will resolve its structure. We will be able to see the distribution of stars and gas within these infant galaxies, mapping their spiral arms, clumps, and tidal tails in stunning detail. We could directly observe the vast outflows of gas being driven by the central black hole's winds, measuring their speed and composition. The ELT might even be able to track the orbital motions of stars in the galactic cores of relatively nearby active galaxies with such precision that we can weigh the central black hole without relying on reverberation mapping, providing a crucial cross-check for our methods. It will turn the faint, blurry blobs we see today into detailed galactic portraits, revealing how black holes and their host galaxies interacted in their formative years. But perhaps the most radical shift in our perception will come from listening to the cosmos rather than just looking at it. The Laser Interferometer Space Antenna, or LISA, is a revolutionary mission that will open an entirely new window onto the universe, the low-frequency gravitational wave spectrum. Unlike their ground-based counterparts LIGO and Virgo, which detect the high-frequency chirps from merging stellar mass black holes, LISA will be a spaceborne observatory consisting of 3 spacecraft flying in a vast triangular formation, millions of kilometers apart. It is designed to sense the long-wave, undulating ripples in spacetime produced by the most massive objects in the cosmos, the merging of supermassive black holes. This is the missing piece of the puzzle in the growth story of these giants. We have strong theoretical reasons to believe that galaxy mergers were commonplace in the early universe, and that when galaxies collided, their central black holes would eventually spiral together and coalesce. But we have never directly witnessed such an event. LISA will change that. It will be sensitive to the gravitational waves emitted when billion solar mass black holes in the early universe finally merge. The signal would be a slow, sinusoidal hum that could last for weeks or even months, growing in amplitude and frequency as the black holes draw closer, culminating in a final, spectacular chirp as they become one. Detecting this cosmic soundtrack would be the ultimate confirmation of the hierarchical growth model. It would provide direct, dynamical evidence that mergers were a key pathway for building the supermassive black holes we see. By analyzing the gravitational wave signals, we could measure the masses and spins of the merging black holes with exquisite accuracy, offering an unparalleled test of general relativity in the strong field regime. Furthermore, LISA could potentially hear the mergers of the elusive intermediate mass black hole seeds, the hypothetical direct collapse black holes that are the crucial link between stellar remnants and supermassive giants. Hearing the birth cry of a supermassive black hole through its gravitational waves would be a discovery on par with the detection of the cosmic microwave background, a direct probe of the most violent and transformative processes in the early cosmos. Together, this trio of next-generation observatories, Roman, the ELT, and LISA, will move us from simply cataloging the light of ancient black holes to understanding their life stories, how they were born, how they grew, and how they shaped and were shaped by the galaxies they called home. This widespread image of a black hole as a cosmic vacuum cleaner, actively sucking in everything in its path with some kind of irresistible force, is one of the most persistent and dramatic misunderstandings in all of science. The reality is far more subtle and, in its own way, even more fascinating. To understand why, we need to separate the object itself from its gravitational influence. At a large distance, the gravitational pull of a black hole is mathematically identical to that of any other object of the same mass. If you were to magically replace our Sun with a black hole of exactly one solar mass, the Earth and all the other planets would not be instantly devoured. Their orbits would remain completely unchanged because the mass at the center of the solar system hasn't changed, only its density has. They would continue their celestial dance in total darkness, but they would not be pulled inward. The gravity you feel from a billion solar mass black hole a million light-years away is no different from the gravity you'd feel from a billion sun galaxy at the same distance. It obeys the same universal law of attraction that Isaac Newton described centuries ago. So, what makes a black hole special isn't the strength of its gravity at a distance, but the incredible intensity of that gravity in an unimaginably small volume. This is where the concept of the event horizon becomes critical. The event horizon is not a physical surface you could crash into like the solid ground of a planet. It is a mathematical boundary, a point of no return defined solely by gravity. It's the invisible sphere around the singularity where the escape velocity equals the speed of light. Since nothing in our universe can travel faster than light, anything that crosses this boundary, be it a speck of dust, a planet, or a photon of light itself, is forever cut off from the rest of the universe. Its future path leads inexorably toward the central singularity. From the outside, we can never see something cross the event horizon. To us, its image would appear to freeze, redden, and fade away due to the extreme gravitational time dilation, as if the universe itself has drawn a final curtain. The real key to understanding how matter falls into a black hole lies in a concept that governs everything from planets orbiting a star to water swirling down a drain: angular momentum. Matter rarely falls directly into a massive object. Just as the planets in our solar system don't fall into the sun, gas and stars in the vicinity of a black hole don't typically fall straight in. They have too much sideways motion, too much orbital energy. They are whipping around the black hole just as Earth orbits the sun. For anything to actually be consumed, it must lose a significant amount of this orbital energy and angular momentum. This is the vital role played by the magnificent structure we've discussed before, the accretion disk. Imagine a comet on a long, elliptical orbit around the sun. For it to fall into the sun, something would have to slow it down, perhaps by brushing against the outer layers of the solar atmosphere, creating friction that steals its orbital energy. This is precisely what happens on a cosmic scale around a black hole, but with far more violence and consequence. Vast clouds of gas and the occasional unlucky star are captured by the black hole's gravity, but their angular momentum forces them into orbiting paths. As this material collects, it forms a flattened, swirling disk, the accretion disk. Within this disk, the physics is anything but simple. The gas and dust at different radii orbit at different speeds, creating immense shear forces. Particles rub against each other, creating frictional heat that can raise temperatures to millions of degrees. This friction is a form of braking. It robs the inner material of its orbital energy, causing it to spiral gradually inward, step by step, like a car slowly circling down a multi-level parking garage. Only after this long, slow dance of energy loss does the material finally reach the innermost stable circular orbit, the last stop before the plunging descent past the event horizon. It doesn't get sucked in, it gets coaxed in, its orbital energy transformed into the blinding light and heat that makes the quasar visible across the universe. This is why a dormant black hole, one without a fuel source to form an accretion disk, can be a completely dark and harmless neighbor on a galactic scale. Without a mechanism to shed angular momentum, matter will simply orbit it forever, held captive by gravity but never consumed, a testament to the fact that a black hole is not an active predator, but a passive, if utterly terrifying, presence in the cosmic ocean. Now, let's shift our focus from the immense gravity and light of these ancient black holes to a more subtle but equally revealing clue: the very chemistry of the cosmic gas that surrounds them. When astronomers point the James Webb Space Telescope at the light from a quasar that existed when the universe was less than 1 billion years old, they aren't just measuring its distance or brightness. They are performing a detailed chemical analysis of the material in its host galaxy. They spread the quasar's light out into a rainbow-like spectrum, looking for the unique dark absorption lines that act as a barcode, each line identifying a specific chemical element that has absorbed some of the quasar's light. For a long time, the expectation was that the first galaxies and the quasars within them would be chemically pristine, composed almost entirely of the two primordial elements forged in the Big Bang, hydrogen and helium. These are the simplest and most abundant elements in the universe, the raw building blocks for everything that followed. The first stars, known as population 3 stars, were predicted to be pure hydrogen and helium giants. So, logic would suggest that the environments around the very first supermassive black holes should be similarly pure, a cosmic throwback to a simpler time before the universe became chemically complex. The data, however, has delivered a stunning surprise. When researchers decoded the spectral barcodes from these incredibly distant quasars, they found the unmistakable fingerprints of elements far heavier than hydrogen and helium. They detected clear signs of carbon, oxygen, nitrogen, and even iron. This is profoundly unexpected. You see, these heavier elements are not produced in the Big Bang. They are forged in two main cosmic forges. The first is the nuclear furnace at the core of massive stars. Throughout their lives, stars fuse hydrogen into helium, and then, in their later stages, they build progressively heavier elements like carbon, oxygen, and silicon. The second and primary source for the heaviest elements like iron and gold is the catastrophic violence of stellar death, the supernova explosion itself, which blasts these newly forged elements out into space. The presence of these metals, as astronomers call all elements heavier than helium, in such an early galaxy means one thing: that an entire generation of stars had already lived out their full life cycles, died in spectacular supernova, and polluted the interstellar gas with their ashes, all before this distant quasar switched on. This discovery completely rewrites the timeline for the early universe's chemical enrichment. It tells us that the first stars did not just form in isolation. They formed, evolved, and exploded with breathtaking speed, seeding their surroundings with the raw materials for planets and indeed for life far earlier than anyone had predicted. To put this into perspective, consider the life cycle of a star. A very massive star might live for only a few million years, a cosmic blink of an eye. But for its ejected elements to then be gathered up into a second generation of star formation, and for those stars to form and then fuel a supermassive black hole that itself grows to billions of solar masses, all had to happen within the first few 100 million years of cosmic history. This is a chain of events of astonishing efficiency. The universe went from a pristine soup of hydrogen and helium to a chemically enriched environment capable of forming rocky planets in less time than it has taken for some of the oldest star clusters in our own Milky Way to complete a single orbit around the galactic center. The heavy elements in the gas around these early quasars are the cosmic equivalent of finding sophisticated tools in the ruins of what you thought was a primitive, first-generation civilization. It forces us to realize that the era of first light was not a slow, stately dawn, but a frenetic and explosive period of creation and destruction, setting the stage for everything that was to come. Now let's take a step back and look at the universe on its very grandest scale. If you could view the cosmos from a God's eye perspective, with galaxies reduced to mere points of light, you wouldn't see a random, scattered assortment. Instead, you would witness an intricate web-like architecture, a vast cosmic tapestry of glittering galaxy clusters and filaments stretching across billions of light-years, separated by enormous, seemingly empty voids. This is the cosmic web, the largest known structure in existence, and its delicate threads are woven not from galaxies themselves, but by the invisible scaffolding of dark matter. Mapping this ethereal structure directly is one of astronomy's greatest challenges, but we have found an ingenious way to chart its invisible contours using the most brilliant beacons from the cosmic dawn, distant quasars. Their incredible luminosity allows them to act as backlights, illuminating the entire cosmic highway between them and us, and in doing so, they reveal the shadowy skeleton of the universe itself. The principle behind this cosmic cartography is known as the Lyman alpha forest, a beautiful and complex phenomenon we touched on earlier. As the intense ultraviolet light from a distant quasar travels through the cosmos for billions of years, it doesn't journey through a perfect vacuum. It passes through the diffuse, mostly invisible gas that traces the cosmic web, countless clouds and filaments of neutral hydrogen. Each time this light encounters one of these clouds, the hydrogen atoms within it greedily absorb light at a very specific wavelength. This creates a sharp, dark dip in the quasar's otherwise smooth spectrum. Because the universe is expanding, each cloud is moving away from us at a slightly different speed. This motion stretches the light waves, a Doppler effect that shifts each absorption line to a unique position in the spectrum. The final result is not a clean, simple rainbow, but a spectrum that looks like it has been chewed up by a cosmic woodpecker. A dense forest of hundreds, even thousands, of individual dark lines, each one a unique barcode representing a single cloud of hydrogen at a specific distance. Decoding this forest is where the true magic happens. Each absorption line is a data point. Its position tells us the distance to the hydrogen cloud that created it, and the depth of the line reveals the cloud's density. When astronomers analyze the spectrum of a single quasar, they are essentially taking a core sample of the universe along that single, precise line of sight. It's like drilling a single, narrow core into the ice of a glacier. You get a detailed history of that one specific spot, but you don't know the full shape of the glacier. This is where massive surveys come into play, transforming this from a study of individual points into a grand, three-dimensional cartography project. By observing not just one, but tens of thousands of quasars spread across the sky, we can take countless core samples. We can look at how the pattern of the Lyman alpha forest changes from one quasar's spectrum to another's. Where the absorption lines are particularly dense and deep in many adjacent lines of sight, it indicates a massive, dense filament of the cosmic web. Where the forest is sparse, it points to one of the great cosmic voids. This is precisely what monumental projects like the Sloan Digital Sky Survey have accomplished. By meticulously cataloging the positions and spectra of hundreds of thousands of quasars, astronomers have been able to piece together a three-dimensional map of the universe's matter distribution on a scale that was once unimaginable. They aren't mapping the bright galaxies we can see. They are using the quasars to map the invisible hydrogen gas that perfectly traces the gravitational potential wells carved out by dark matter. The final maps are breathtaking. They reveal a universe that looks like a colossal neural network or a froth of soap bubbles on a cosmic scale, with galaxies clustered along the filaments and intersections of the web and vast, empty deserts in between. These maps provide the most compelling visual evidence we have for the existence of dark matter and the hierarchical model of cosmic structure formation, showing us that the universe, in its largest dimensions, is a web of shadows illuminated by the most distant and brilliant lights in the cosmos. Yet, even as our cosmic cartography reaches new heights, it forces us to confront a truly ultimate frontier, a boundary not just of distance but of time itself. We've marveled at black holes from when the universe was 600 million years old, but what about the very first one? What is the absolute limit, the farthest back in time we could ever hope to see a black hole? The answer lies buried in the deepest, most profound chapter of cosmic history, a period known as the Dark Ages. This was the era before the first stars, a time when the universe was a vast, silent, and utterly black sea of cooling hydrogen and helium gas. There were no light sources, no quasars, no galaxies, just the fading afterglow of the Big Bang and the slow, gravitational simmering of dark matter. To observe a black hole from this epoch is the ultimate goal, but it's a goal that pushes against a fundamental cosmic veil. The Dark Ages represent a barrier because without luminous stars or active galactic nuclei, there is simply no light for our telescopes to collect. The universe was, for the first several hundred million years, a perfectly dark and opaque room. We cannot see into it with traditional astronomy. We can only infer what must have been happening based on the structures that emerged when the lights finally switched on. This profound darkness, however, is precisely where one of the most exotic theories in cosmology takes root. What if the very first black holes weren't born from dying stars at all, but were instead forged in the unimaginable furnace of the universe's first moments? These hypothetical objects are known as primordial black holes, and their potential existence rewrites the entire opening chapter of cosmic structure. The theory proposes that in the incredibly dense, seething soup of the infant cosmos, just instants after the Big Bang, there were tiny, random quantum fluctuations in density. Most of these fluctuations were minor, but some could have been intense enough that the gravitational pull in a particular patch of space was so overwhelming that the region collapsed directly into a black hole. This wouldn't require a star or any complex astrophysics. It would be a direct result of the raw, violent energy of creation itself. A primordial black hole could have been born with almost any mass, from something lighter than a paperclip to an object thousands of times more massive than our Sun. If they formed with the right mass and in sufficient numbers, they could have served as the ready-made seeds for the supermassive black holes we find later, providing a colossal head start that solves the timing problem once and for all. The ongoing search for these elusive primordial objects is a testament to scientific creativity, as astronomers must look for their influence through indirect, subtle signatures since they emit no light of their own. One fascinating method involves hunting for the telltale flicker of a phenomenon called gravitational microlensing. If a primordial black hole were to drift silently between a distant star and our telescopes on Earth, its gravity would act as a tiny, temporary lens, bending the star's light and causing it to briefly brighten in a very specific, predictable pattern. Surveys that monitor millions of stars for these fleeting brightening events have placed stringent limits on how many primordial black holes of certain mass ranges could be drifting through our galactic neighborhood. Another approach listens for the cosmic echoes of their demise. Very small primordial black holes, according to Stephen Hawking's theory, would have evaporated over the age of the universe through the emission of Hawking radiation. Their final moments would be a spectacular burst of high-energy gamma rays. While we haven't definitively detected such a signal, astronomers continue to scour gamma-ray data for these unique, explosive fingerprints of a tiny black hole's death cry. Perhaps the most profound evidence could come from the Future Laser Interferometer Space Antenna, or LISA, which might be sensitive enough to hear the gravitational wave hum from the mergers of intermediate mass primordial black holes in the early universe, a sound that would be unmistakable proof of their existence. Ultimately, the search for the first black hole is a journey to the very edge of physics, a quest to witness the moment when the chaotic infancy of the cosmos first gave rise to a gravitational singularity. Whether they were the stellar remnants of the very first colossal population 3 stars, or the primordial black holes born from the Big Bang's own density fluctuations, their formation marked a pivotal transition. It was the moment the universe learned how to create a perfect gravitational trap, an object so simple in its description yet so profound in its implications. Finding evidence of a black hole from the Dark Ages would be like discovering the first spark that ever flickered in a universe of endless night. It wouldn't just break a distance record, it would shatter our understanding of cosmic origins, revealing the initial conditions that set the stage for every galaxy, star, and planet that was ever to follow. The limit of our vision is not just a technical challenge, it is the horizon of our fundamental knowledge, and beyond it lies the answer to how the cosmos built its very first engines of gravity. The connection between a supermassive black hole and its host galaxy is far more intimate and profound than a simple landlord-tenant relationship. It is a deep, fundamental symbiosis that has shaped the universe as we see it today. For decades, astronomers viewed these cosmic giants as fascinating but largely incidental features, like a decorative fountain in the center of a city. But a series of groundbreaking discoveries in the late 1990s and early 2000s revealed something astonishing. The mass of a galaxy's central supermassive black hole is intricately linked to the properties of the galaxy itself, specifically the mass of its central bulge, the dense, spherical concentration of stars at its core. This is the observed correlation that forms the bedrock of the co-evolution theory. It turns out that the size of the central black hole's gravitational anchor is, on average, about 1/1000th of the mass of the surrounding stellar bulge. This ratio, this cosmic scaling law, appears to hold true across a vast range of galaxy types, from small, disordered spirals to giant, featureless ellipticals. It's as if the universe has a rule: for every 1,000 stars that form in the galactic center, one solar mass must be sequestered away in the central black hole. This is not a coincidence, it is a signature of a shared history, a story of growth and regulation written in the fundamental properties of galaxies across cosmic time. The evidence for this co-evolution is compellingly statistical. When astronomers painstakingly measured the masses of supermassive black holes in nearby galaxies using the motion of stars or gas to weigh them, and then compared those masses to the velocity dispersion of stars in the galactic bulge, they found a tight, predictable relationship. The faster the stars in the bulge are moving, the more massive the central black hole. Since the speed of those stars is a direct measure of the depth of the galaxy's gravitational well, this relationship directly ties the black hole's growth to the gravitational potential of its home. This correlation is far too precise to be random. It strongly suggests that the processes that build a galaxy's central bulge are through mergers, rapid star formation, and the accretion of gas are somehow communicating with the processes that feed the central black hole. They are not growing independently, they are growing together, locked in a gravitational dance where each influences the other's development. This discovery transformed our understanding of galaxy evolution. The central black hole was no longer a silent passenger. It was an active participant in the galactic construction project, its growth calibrated to the overall growth of the stellar city around it. But how does this communication happen? The black hole and the galaxy don't physically touch. The answer lies in the concept of feedback, a powerful self-regulating mechanism that has become an essential, non-negotiable ingredient in all modern simulations of galaxy formation. Imagine a growing galaxy, rich with cold gas, forming new stars at a ferocious rate. This same gas also funnels toward the center, feeding the supermassive black hole and igniting its quasar phase. For a time, there is explosive growth in both stars and the black hole, but then the black hole unleashes its power through intense radiation from its accretion disk, and most powerfully through its relativistic jets. It floods the galaxy with a colossal amount of energy. This energy does two critical things. First, it heats the vast reservoirs of cold gas, the raw fuel for star formation. Hot gas cannot collapse to form new stars, it's too energetic. Second, in more extreme cases, it can drive massive galactic winds, physically blasting that gas right out of the galaxy entirely. This black hole feedback acts as a cosmic thermostat. It quenches star formation, effectively shutting down the galaxy's primary growth engine and preventing it from becoming unrealistically large in simulations. The black hole, in its most active and brilliant phase, is ultimately responsible for its own starvation and the transition of its host galaxy into a quiet, mature, and redder state. This feedback loop solves a major puzzle that plagued cosmologists for years. Without including black hole feedback in their sophisticated computer models, simulations consistently produced galaxies that were far too massive and had far too many stars compared to what we actually observe in the real universe. The models would create blue, star-forming monsters that bore little resemblance to the diverse population of galaxies we see around us. But when physicists programmed the energy output from growing supermassive black holes into these simulations, something remarkable happened. The virtual galaxies began to look right. The feedback would periodically blast away gas, regulate star formation, and produce the correct distribution of galaxy sizes, colors, and shapes. It would create the red, dead elliptical galaxies we see, whose star formation was quenched long ago. The correlation between black hole mass and bulge mass emerged naturally from these models as a direct consequence of this balancing act. The galaxy builds the bulge and feeds the black hole, and the black hole, in turn, uses that energy to regulate the galaxy's future growth. It is a powerful, self-correcting cycle that has been operating since the cosmic dawn, ensuring that galaxies and their central black holes evolve in lockstep, sculpting the large-scale structure of the universe into the beautiful and organized cosmos we observe today. But for all their power and seeming permanence, even these cosmic titans are not eternal. Their reign, which began in the fiery forge of the early universe, will eventually come to a slow, quiet, and profoundly strange end in the far, far future. To understand their ultimate fate, we must journey beyond the classical physics of Einstein and descend into the bizarre quantum realm that governs the very small. It was here that Stephen Hawking made his most revolutionary discovery, proposing a mechanism that forever changed our view of black holes. They can, in fact, evaporate. This process, now known as Hawking radiation, arises from the unpredictable nature of empty space itself. According to quantum mechanics, a perfect vacuum isn't truly empty. It's a seething, bubbling sea of virtual particles. These are pairs of particles and their antimatter counterparts that spontaneously pop into existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and returning the energy, a constant dance of creation and destruction happening everywhere all the time. Now, imagine this quantum froth occurring right at the precipice of a black hole's event horizon. One of these virtual particle pairs appears. In a fantastically rare but consequential event, the two particles don't annihilate each other immediately. Instead, one particle falls across the event horizon, forever lost to the black hole while its partner escapes into space. From the perspective of an outside observer, the black hole has just emitted a particle. To conserve energy, the particle that fell in must have had negative energy. This sounds like science fiction, but in the warped geometry just outside the event horizon, this is a possible outcome. The net result is that the black hole has lost a tiny, tiny amount of mass, converted into the energy of the escaped particle. This is Hawking radiation, a slow, relentless trickle of particles bleeding away from the black hole, causing it to very, very gradually evaporate. For a supermassive black hole, this process is almost unimaginably slow. The more massive the black hole, the larger its event horizon and the weaker its gravitational gradient at the boundary, making it harder for this quantum theft to occur. A black hole with the mass of our Sun would take far, far longer than the current age of the universe to evaporate significantly. But for the universe's most distant, most massive black holes, weighing billions of solar masses, the timeline is stretched into the realm of the truly inconceivable. Projecting forward trillions upon trillions of years into the future, we enter the final, degenerate eras of the cosmos. All stars will have long since burned out, their ashes scattered. Galaxies will have evaporated as their stars drift apart in an ever-accelerating, expanding universe. The cosmos will be a profoundly dark and cold place, populated only by the skeletal remnants of stars, white dwarfs, neutron stars, and the silent, lurking black holes. One by one, over epochs that dwarf the current age of the universe, the smaller black holes will begin to vanish. As a black hole evaporates, it doesn't just shrink quietly. In its final moments, when its mass becomes very small, the process accelerates violently. The Hawking radiation temperature rises dramatically as the black hole loses mass, and it ends its life in a spectacular burst of high-energy gamma rays, a final flash of light in an otherwise dark cosmos. The stellar mass black holes will blink out of existence first, followed by the intermediate mass ones. But the supermassive black holes, the ancient giants we've been discussing, will endure. They will be the last significant structures, the final monuments to a once vibrant universe. In a cosmos that is cold, dark, and stretched thin by expansion, these gravitational leviathans will be the sole keepers of immense mass and order. They will continue their slow evaporation for timescales so vast that numbers like 1 trillion years become a vanishingly small unit. Ultimately, however, even their time will come. The last supermassive black hole in the universe will, after an eternity of solitude, itself begin to heat up. Its Hawking radiation will intensify from a faint whisper to a rising scream of particles, and in one final, magnificent burst of energy, it will vanish. With its disappearance, the era of black holes will be over. The universe will be left with a dilute sea of subatomic particles and radiation, cooling toward absolute zero in an endless, featureless expansion. The journey that began for these distant black holes in the frantic energy of the cosmic dawn will thus conclude in the absolute silence of the cosmic end, their long evaporation a final, quiet testament to the impermanence of all structures, no matter how powerful or ancient they may seem. So, while Hawking radiation seals the ultimate fate of all black holes, its timeline is where the true cosmic perspective comes into play. The rate at which a black hole evaporates isn't constant. It's governed by a beautifully simple yet profound rule. The smaller the black hole, the faster it evaporates. This is because the intensity of Hawking radiation is tied to the black hole's temperature, and that temperature is inversely proportional to its mass. A stellar mass black hole is incredibly cold, just a tiny fraction of a degree above absolute zero, so its evaporation is a barely perceptible whisper. But as a black hole loses mass, it gets hotter. As it gets hotter, it radiates more energy. As it radiates more energy, it loses mass even faster. This creates a runaway process, a positive feedback loop that ensures the final moments of any black hole's life are a spectacular, explosive crescendo. Now, let's apply this to the ancient supermassive black holes we've been exploring. Take one with a mass of 1 billion suns, like the one at the heart of the distant quasar J0313-1806. The sheer scale of the numbers involved here is almost impossible for the human mind to grasp. The current age of our universe is about 13.8 billion years, which is roughly 10 to the power of 10 years. A billion solar mass black hole, however, would take approximately 10 to the power of 90 years to completely evaporate via Hawking radiation. To understand how immense this number is, consider that there are only an estimated 10 to the power of 80 atoms in the entire observable universe. We are talking about a time frame that is 10 billion times longer than the number of atoms in existence. It is a duration so astronomically vast that the current age of the cosmos is less than a single, fleeting heartbeat in a lifespan that spans eons beyond counting. This timescale places the evaporation of these giants squarely in the speculative future eras of the cosmos, long after all stellar formation has ceased and the last stars have faded to cold black dwarfs. In this distant epoch known as the Dark Era, the universe will be a profoundly different and lonely place. Galaxies will have evaporated as their constituent stars drift apart due to the relentless acceleration of cosmic expansion. The universe will be an increasingly cold and dilute sea of subatomic particles and radiation, cooling ever closer to absolute zero. Against this backdrop of ultimate stillness and darkness, the supermassive black holes will endure. They will be the last monuments of ordered mass, the final vestiges of a once vibrant and structured cosmos. For durations that defy human comprehension, they will be the only significant landmarks in an otherwise featureless void, slowly and imperceptibly converting their immense gravitational mass into a faint whisper of radiation. This incredible longevity means that for all practical purposes, and from our current vantage point in cosmic history, these supermassive black holes are effectively permanent fixtures. They are not transient phenomena, they are among the most stable and long-lasting structures the universe will ever produce. Their eventual demise, while a fascinating theoretical endpoint, is so immeasurably far in the future that it has no bearing on their role as the dominant gravitational anchors shaping cosmic evolution for trillions upon trillions of years to come. Their story, which began in the frantic, energetic forge of the cosmic dawn, will continue through the stelliferous era of stars and galaxies and deep into the degenerate and dark eras that follow. Their silent, slow evaporation, a final, quiet testament to the impermanence of all things, played out on a timescale that truly defines the word eternity. Our journey to the edge of the observable universe has taken us across billions of light years and billions of years, back to a time when the cosmos was a raw, volatile, and rapidly assembling place. We began by grappling with the sheer scale of these distances, understanding that to observe a distant black hole is to look back in time to the universe's chaotic infancy, a direct window into the era of cosmic dawn. The very existence of these objects, like the record-holding quasar J0313-1806 with its billion solar mass heart, presents a monumental challenge to our understanding of physics, forcing us to consider radical ideas like direct collapse seeds and super-Eddington accretion to explain how such giants could form in what was, cosmically speaking, the blink. They are not merely ancient relics, they are glaring clues that the early universe operated under a different, more extreme set of rules, pushing us to rewrite the story of cosmic structure formation. Beyond the puzzle of their origins, we've seen how these distant monsters are far more than just gravitational curiosities. They act as brilliant cosmic lighthouses, their quasars cutting through the primordial fog and illuminating the vast, invisible cosmic web, allowing us to map the distribution of dark matter itself. At the same time, they are powerful architects shaping the evolution of the universe through their immense energy output. Their relativistic jets and intense radiation can heat galactic gas, blow it clean out of a galaxy, and permanently quench star formation, effectively dictating the life and death of their celestial homes. This intricate feedback loop, this cosmic symbiosis between black hole and galaxy, reveals a universe where the largest structures are built through a delicate and violent dance between creation and destruction, gravity and light. Yet, for all we have uncovered, profound mysteries remain. The true nature of the very first black hole seed is still hidden from us, lost in the darkness of the cosmic dark ages. The black hole information paradox continues to pit the two great pillars of modern physics against each other, with these ancient objects serving as the ultimate testing ground. The latest data from the James Webb Space Telescope is simultaneously answering old questions and presenting us with new, unexpected ones, showing us host galaxies that are smaller and more chaotic than our models predicted. The frontier of our knowledge is constantly being pushed, and with future observatories like the Roman Space Telescope, the Extremely Large Telescope, and the Gravitational Wave Detector LISA, we are on the verge of an even deeper revolution, one that will allow us to hear the collisions of these giants and see their host galaxies in stunning detail. Ultimately, this journey into the deepest reaches of space and time is more than a catalogue of incredible facts. It is a profound exercise in understanding our own place in the cosmos. To study these distant, ancient leviathans is to trace our own cosmic lineage back to its very origins. The heavy elements we discovered in their surroundings, the carbon, oxygen, and iron, are the very same elements that make up our world and our bodies, forged in the hearts of those first stars and scattered by their explosive deaths, later gathered up to form our solar system and eventually us. We are connected to these far-off monsters by the very fabric of our being. They are part of the story that led to a universe capable of contemplating itself, of asking questions, and of reaching out across the vastness to uncover its own secrets. They remind us that we are not just living in the universe, we are a conscious part of its ongoing, epic narrative. We would love to hear which of these 30 facts reshaped your perspective the most. Was it the unimaginable timescales, the growth paradox, or their role as cosmic architects? Let us know in the comments below, and if you enjoyed this deep dive into the mysteries of space, be sure to subscribe so you don't miss our next exploration into the wonders of the cosmos.